Hello there, and welcome to Midnight Geography. Tonight we'll drift into the quiet landscapes of Ohio, a place where ancient ice once carved its story into stone. Ohio's geography is a conversation between forces. It sits where glaciers paused and melted, where great waters divided their paths, where limestone remembers warm, shallow seas. This is land shaped by ice, by rivers that couldn't decide which ocean to seek. Ohio is proof that flat places can hold depth, that crossroads collect stories. If you enjoy these peaceful geographical explorations, consider liking and subscribing. It helps other curious minds find their way here too. But for now, let's begin. Campbell Hill rises near the town of Bellefontaine, marking Ohio's highest point at precisely 1,549 feet above sea level. The summit itself sits unremarkably among farmland, distinguished more by what it represents than by any dramatic elevation. Stand there, and you rise only about 300 feet above the surrounding countryside. The landscape falls away so gently you might not notice the descent. This is Ohio's version of a mountain, shaped not by the violent uplift that creates true peaks, but by the patient work of ice. The glaciers that covered most of Ohio simply deposited more material here, building the land higher grain by grain, stone by stone. There's something quietly profound about a high point that doesn't tower or dominate, that asks no attention for itself. Campbell Hill reminds us that prominence is relative, that significance doesn't require spectacle. A small monument marks the spot, visited by geography enthusiasts who understand that extremes tell only part of a landscape's story. Just 65 miles from Campbell Hill, the Ohio River defines the state's lowest point at 455 feet elevation along the southern border. This modest vertical span of roughly 100 feet encompasses Ohio's entire topographic range. Think about that. Many individual mountains elsewhere possess greater relief than Ohio's highest and lowest points combined. The state slopes so gradually from north to south that you could drive its length without truly noticing the descent. This gentle gradient speaks to Ohio's glacial heritage, those massive ice sheets that smoothed and filled and leveled the northern terrain. The southern unglaciated region offers more drama, but even there the land rises and falls with restraint. What emerges from these numbers is a portrait of subtlety, a landscape that doesn't shout its features, but whispers them. The distance between highest and lowest points feels almost conversational, as though the land is simply suggesting possibilities rather than insisting upon them. The glacial grooves on Kelly's Island stretch across exposed limestone like the longest scratch in stone you'll ever witness. Individual grooves measure up to 15 feet deep, 35 feet wide, and extend for more than 400 feet. These are not subtle marks. These are the Earth's memory made visible, carved when unimaginable weight dragged rock across rock. The grooves run parallel, all pointing southwest, recording the glacier's direction with geological precision. You can walk among them, trace their depths with your hands, feel the texture of stone that hasn't changed in 18,000 years. The limestone beneath was once a tropical sea floor, and now it bears the scars of ice a mile thick. This juxtaposition of warm water origins and frozen violence creates a strange temporal vertigo. Stand in these grooves, and you stand in a conversation between ages, between climates that couldn't be more different. The grooves are deep enough that they collect rainwater, supporting small ecosystems in their troughs, moss and lichen finding homes in wounds inflicted by the Pleistocene. These particular grooves were carved approximately 18,000 years ago by the Wisconsin Glacier, the last great ice advance to cover northern Ohio. The glacier didn't simply pass over this spot. It ground across it with relentless patience, dragging embedded boulders and gravel like the world's largest piece of sandpaper. The scratches all point southwest, because that's where the ice was flowing, pushed by its own accumulating weight far to the north. Each groove represents countless smaller rocks caught in the glacier's base, held against the limestone as the ice crept forward at a rate measured in feet per year. The force required to carve these features defies comfortable comprehension. We're talking about ice thick enough to have its own weather systems, heavy enough to depress the Earth's crust. And yet the process was slow, almost gentle in its patience. No sudden violence created these grooves, just thousands of years of consistent pressure. The result is a textbook example of glacial striation, so clear that geology students study these particular marks from all over the world. Ohio sits atop 5 distinct layers of glacial till, each representing a separate ice advance during different periods over the past 2.5 million years. These layers aren't visible from the surface, but drilling and excavation reveal them. Different colors, different compositions, each one telling the story of its particular glacial period. The oldest lie deepest, buried under the deposits of later advances. The youngest form the surface soil across much of northern Ohio. Between these till layers sometimes lie thin deposits of organic material, evidence of the brief, warm periods when forests grew between ice ages. Think about that sequence. Ice, warmth, forest, ice again, repeated across geological time. Each glacial advance scraped away much of what came before, but not everything. Fragments remain, pressed between layers like pages in an ancient book. The till itself is a mixture of clay, sand, gravel, and boulders, unsorted and unstratified, dropped in place as the ice melted. The Allegheny Plateau in southeastern Ohio covers roughly 1/3 of the state and was never touched by glaciers. This unglaciated region presents a completely different landscape from the flattened northern plains. Here, the valleys are deeper, cut over millions of years by flowing water rather than carved in millennia by moving ice. The ridges run in parallel lines, following the geology of tilted sedimentary layers. Forests here have deeper roots in time, quite literally. The soil developed over eons rather than over the mere thousands of years since the last glacier. The streams follow ancient paths, their courses determined by bedrock structure rather than by glacial debris fields. Stand in southeastern Ohio, and you're experiencing topography that predates the ice ages, a landscape older than the Great Lakes, older than the modern configuration of rivers. The contrast with glaciated Ohio is striking. Where ice smoothed the north into gently rolling farmland, the south remains rugged, resistant, carved, but not erased by time. This is what Ohio looked like before the ice came, this texture of ridge and hollow. Ash Cave opens like a massive amphitheater in the Hocking Hills, its horseshoe-shaped recess spanning 700 feet wide and 90 feet deep. The overhang creates a shelter large enough to hold thousands of people, and indeed it did shelter indigenous peoples for millennia before European settlement. The cave, though technically a recess rather than a true cave, formed through erosion, as softer middle layers of blackhand sandstone weathered away faster than the harder caprock above. Water played the primary role, seeping through cracks and freezing in winter, spalling and loosening the stone fragment by fragment. The delicate waterfall that spills over the lip year-round adds to the cave's depth with each passing century, though the pace is measured in geological time. The floor of Ash Cave remains dry, protected by the deep overhang, while the waterfall streams down beyond the shelter's edge. In winter, the falls freeze into curtains of ice, transforming the scene into something almost sculptural. The acoustics inside are remarkable, voices echoing softly off the curved sandstone walls. Old Man's Cave sits just 3 miles from Ash Cave, another sandstone recess formation in the Hocking Hills, but with a more intimate scale and a curious human story attached to its name. The cave earned its name from Richard Roe, a hermit who lived in this shelter in the early 19th century until his death. Local legend claims his dog maintained vigil at his grave nearby for years afterward, though separating truth from folklore becomes difficult across 2 centuries. The cave itself features a spectacular upper and lower falls system, with Queer Creek tumbling through a narrow gorge before disappearing underground. The sandstone walls display the characteristic honeycomb weathering pattern common to Blackhand sandstone, where differential erosion creates pockmarked surfaces. A natural stone bridge spans the gorge at one point, formed where harder layers resisted erosion, while softer stone beneath washed away. Hemlock trees grow in the cool, moist microclimate of the gorge, their dark foliage adding to the shadowed, secretive atmosphere that perhaps appealed to a man seeking solitude. The Blackhand sandstone formation near Newark once displayed a mysterious petroglyph of a dark hand carved into the cliff face by unknown hands hundreds of years ago. The image gave the formation its name and fired imaginations for generations. Unfortunately, canal construction in the 1820s destroyed most of the original sandstone cliff, including the best examples of the hand petroglyphs. Fragments remain, carefully preserved, but the full impact of the original carving is lost to progress. What remains unclear is who created the petroglyph and what it signified. Theories range from indigenous boundary markers to ceremonial significance, but the sandstone keeps its secrets. The surviving remnants show clear evidence of deliberate carving, the hand shape unmistakable despite weathering. The sandstone itself formed from ancient beach sands approximately 350 million years ago, meaning the rock predates the carving by an almost incomprehensible span of time. Someone stood before this particular cliff face centuries ago and chose this spot, this stone, to leave their mark, never knowing their canvas would eventually be destroyed by people seeking an easier path for water to flow. The Serpent Mound undulates across the landscape for 1,348 feet, averaging 3 feet in height, forming the largest serpent effigy on Earth. The earthwork depicts a snake with an open mouth, its body coiling in 7 distinct curves before tapering to a tightly wound tail. What makes Serpent Mound particularly fascinating is how little we truly understand about it. The effigy's age remains debated. Radiocarbon dating has produced confusing results, with some evidence suggesting construction around 300 BCE during the Adena culture, other data pointing to approximately 1000 CE during the Ford Ancient culture. The purpose is equally mysterious. Some researchers note astronomical alignments, particularly how the serpent's head appears to point toward the summer solstice sunset. Others suggest it had ceremonial or religious significance we can't fully reconstruct. The effigy occupies a plateau above Brush Creek, and its elevated position makes the serpent visible from surrounding ridges, but not from the air. It was built for viewers on the ground. The builders moved thousands of cubic yards of earth and clay to construct this figure, shaping it with such precision that its form remains clear 13 centuries or more after its creation. The effigy's head aligns with the summer solstice sunset, though whether this astronomical connection was intentional remains one of many questions surrounding Serpent Mound. From the serpent's open mouth, an observer watching the western horizon on the longest day of the year would see the sun set in direct alignment with the mound's orientation. Such precision doesn't happen accidentally when you're moving Earth by the basketful. Other potential alignments exist as well. Some researchers suggest the coils correspond to lunar cycles or other celestial events. The challenge with these theories is determining which alignments are intentional and which are coincidental. Ancient peoples were certainly capable of sophisticated astronomical observation, and many earthworks across the Americas demonstrate clear celestial connections. Yet without written records or oral traditions that survived to the present, we're left interpreting physical evidence that allows multiple explanations. What we can say with confidence is that Serpent Mound's builders possessed sophisticated surveying and engineering skills, creating curves and proportions that remain harmonious across the effigy's enormous length. Someone planned this carefully, whether for astronomical, religious, or other purposes we may never fully understand. Beneath Serpent Mound lies a 256-million-year-old impact crater, roughly 4 miles in diameter, caused by a meteorite that struck during the Permian period when this region was part of a shallow tropical sea. The impact fractured and deformed the underlying rock in distinctive patterns that geologists didn't recognize until satellite surveys in the 1980s revealed the circular structure. The crater itself is completely buried under hundreds of feet of younger sedimentary rock and glacial deposits, invisible from the surface except through geophysical analysis. The coincidence of having North America's largest serpent effigy built directly atop a massive impact crater strikes many as too strange to be accidental. Yet there's no evidence the mound builders knew about the crater below. The fractured bedrock did create unusual rock formations in the area, and perhaps these surface expressions of deep structure attracted the attention of whoever chose this site. The crater dates to an era when Ohio lay near the equator, when primitive reptiles were just beginning to dominate terrestrial ecosystems, long before dinosaurs, longer still before humans. Whatever massive object struck here vaporized on impact, leaving only its scar in the bedrock. Lake Erie forms Ohio's entire northern border, stretching 241 miles from the Pennsylvania line to the Michigan boundary, holding 116 cubic miles of water that averages only 62 feet in depth. This shallowness makes Erie unique among the Great Lakes, giving it characteristics more similar to a massive shallow bay than to the deep inland seas of Superior or Michigan. The shallow water warms quickly in summer, sometimes reaching temperatures above 70 degrees, warm enough for comfortable swimming. It also freezes more readily in winter. During severe cold snaps, Erie can freeze almost completely, becoming a vast white plain that effectively closes the lake to shipping. The shallow depth means light penetrates to the bottom across much of the lake, supporting extensive plant growth and creating remarkably productive fisheries. But this same shallowness makes Erie vulnerable to environmental problems. Pollutants don't get diluted into deep water, but concentrate in the shallow volume. The Western Basin, where Ohio's shoreline lies, is shallowest of all, averaging just 24 feet. Here, the lake is less a lake and more a wetland, spread across an enormous area, its reedy shallows providing critical habitat for migrating waterfowl. The Bass Islands scatter across Lake Erie's western basin in an archipelago of more than 20 limestone fragments, though only 3 support significant year-round populations. South Bass, North Bass, and Middle Bass are the primary inhabited islands, each barely large enough to warrant the designation, yet each maintaining distinct identities and communities. The smaller islands range from acre-sized rocks that barely break the surface to slightly larger formations that support a few summer cottages. Water levels in Lake Erie fluctuate based on precipitation patterns across the entire Great Lakes Basin, and these fluctuations dramatically affect the islands. In low water years, channels between islands narrow, and reefs emerge that are normally submerged. In high water years, beaches shrink and docks stand waist deep. The islands themselves are limestone bedrock, the same Devonian formation that underlies Detroit, with thin soil supporting hardy vegetation adapted to the island's exposure to wind and waves. Winters can be harsh, with ice cutting the islands off from the mainland for weeks at a time. The permanent islanders form tight-knit communities by necessity, knowing they're choosing a life defined by water and weather. Kelly's Island spans 4.4 square miles of limestone bedrock, making it the largest American island in Lake Erie, yet it supports a year-round population of fewer than 150 souls. In summer, this population explodes as tourists arrive by ferry, swelling the island to thousands of visitors on busy weekends. But come September, the crowds depart, the ferries reduce their schedules, and the island returns to its small community of hardy permanent residents. The scale of seasonal variation creates two completely different islands occupying the same space. Summer Kelly's Island is bustling, commercial, crowded with golf carts and bicycles and tourists seeking the glacial grooves in the beaches. Winter Kelly's Island is quiet, contemplative, sometimes cut off entirely, when ice closes the ferry route and only the most adventurous ice fishermen venture across the frozen expanse. The limestone bedrock provides good drainage, preventing the island from becoming swampy, despite sitting barely above lake level. Quarrying operations once dominated the island's economy, extracting the high-quality limestone, though now the industry has mostly ceased and nature slowly reclaims the worked-over landscape. The population numbers reflect a truth about island living. It's a choice that selects for certain temperaments. South Bass Island contains Perry's Victory and International Peace Memorial, a Doric column rising 352 feet above the island to commemorate the War of 1812's Battle of Lake Erie. The memorial's height makes it the tallest such structure in the world, visible for miles across the lake's flat waters. Climbers who ascend the interior staircase or take the elevator emerge at an observation deck commanding views across the entire island archipelago and far into Canadian waters beyond. The memorial honors not just the American victory, but the lasting peace between the United States and Canada, celebrating the world's longest undefended international border. This dual purpose transforms what could have been a simple victory monument into something more contemplative, acknowledging that the real achievement is not the battle won, but the peace maintained. The memorial's location on South Bass Island isn't arbitrary. The Battle of Lake Erie took place in these waters, with Perry commanding the American fleet from the nearby shore before sailing out to confront the British. The limestone beneath the monument is the same stone that forms the lake bottom, that breaks the surface as these islands, that extends beneath Detroit and Windsor. Middle Bass Island once housed the Golden Eagle Winery, which in the 1880s claimed to be the world's largest wine production facility, with operations processing grapes from vineyards covering much of the island. The winery utilized massive limestone caves carved beneath the island specifically for wine storage. These caves maintained constant temperatures between 55 and 60 degrees Fahrenheit, perfect for aging, with natural humidity levels ideal for preventing cork drying. The caves required no artificial cooling or heating, just the thermal mass of solid limestone, regulating conditions year-round. Workers carved these storage chambers by hand, removing limestone in blocks that were then used for construction, creating useful space while harvesting building materials simultaneously. The wine industry declined on Middle Bass after Prohibition devastated the market, though some winemaking continues. The caves remain, now used for aging and storage by a much smaller operation. Walking through these caverns, You're struck by the sheer volume of earth removed to create the space, the ambition required to envision excavating stone chambers beneath an island with such certainty that wine production would justify the investment. The Marblehead Peninsula extends into Lake Erie like a limestone finger pointing north. Its bedrock, composed almost entirely of Columbus limestone, formed 400 million years ago. This ancient stone began as calcareous mud and shell fragments accumulating on a shallow tropical seafloor, compressed and lithified over eons into the hard gray rock, now quarried extensively throughout the region. The peninsula's name comes from this limestone's appearance when polished, a smooth, marble-like finish that made it valuable for building construction and decorative purposes. Quarrying has removed billions of tons from Marblehead over nearly 2 centuries of continuous operation. The quarries create vast open pits, their walls exposing the limestone's horizontal bedding planes, each layer representing a different period of deposition in that ancient sea. Some quarries have been abandoned and allowed to fill with groundwater, creating deep, clear lakes with vertical walls dropping into invisible depths. The active quarries continue removing stone, their operations carving new landscapes into bedrock older than trees, older than insects, created before vertebrates had colonized land. Quarries near Marblehead have extracted limestone continuously since the 1830s, removing material that's been shipped across the Midwest to construct buildings in cities from Chicago to Detroit. The stone's quality made it particularly prized for foundations and exterior facades. And if you examine 19th century architecture in Great Lakes cities, you're likely seeing Marblehead limestone. The scale of extraction is difficult to comprehend. Quarries have removed entire hilltops, excavated pits hundreds of feet deep, created negative landforms where positive ones once existed. Each cubic yard of stone extracted is gone forever. The bedrock's 400 million year accumulation removed in an afternoon by modern equipment. Yet even after nearly 2 centuries of intensive quarrying, limestone deposits remain extensive. The formation is thick, widespread, and economically viable to extract. The quarries represent a peculiar human relationship with geological time, taking stone that formed before land plants existed and using it to build structures that will crumble to dust in mere centuries. We extract permanence to create impermanence, borrowing from deep time to serve brief needs. The Cuyahoga River meanders in remarkable fashion, flowing both north and south from its highest elevation, creating the unusual spectacle of a river that seems unable to decide its direction. From headwaters near Hamden, the river initially flows southward, away from Lake Erie, eventually turning in a great arc and finally choosing to flow north, reaching the lake at Cleveland after traveling roughly 100 miles through only 30 miles of linear distance. This extravagant meandering gives the river its name, from a Native American word meaning crooked river. The Cuyahoga's indecisive path results from its valley's glacial origins. The river occupies a meltwater channel carved during the ice sheet's retreat, following the most convenient path through debris left by glaciers. In some places, the river cuts through solid bedrock. In others, it wanders across flat till plains deposited by ice, creating oxbow bends and meanders that shift gradually over time. The valley walls in places rise high enough to create a gorge, while elsewhere the river spreads across floodplains. The Cuyahoga's journey is inefficient by design, shaped by ice that melted 18,000 years ago, but still controls the river's modern course. The Cuyahoga caught fire repeatedly throughout the industrial era, at least 13 documented times between 1868 and 1969, a grim distinction for any river. Oil slicks, industrial waste, and debris accumulated on the water's surface, creating conditions where a single spark could ignite flames that spread across the river itself. The 1969 fire, though not the largest or most destructive, became symbolically significant because it occurred at a moment when environmental awareness was rising across the nation. Photographs of a burning river shocked the public consciousness in ways that statistics about pollution never could. Water is supposed to extinguish fire, not fuel it. The image violated something fundamental in our understanding of the natural order. This particular blaze helped catalyze the environmental movement, contributing to the creation of the Environmental Protection Agency and the passage of the Clean Water Act. Today, the Cuyahoga runs clear enough to support fish populations and recreational use, a remarkable recovery that demonstrates both how severely we can damage ecosystems and how resilient they can be when given opportunity to heal. The river still meanders through the same valley, but it no longer carries the burden of being so polluted it could burn. Brandywine Falls drops 65 feet over a ledge of Sharon conglomerate in Cuyahoga Valley National Park, the water spreading into a delicate veil during low flows and thundering into a substantial cascade after heavy rains. The bedrock over which it falls formed approximately 320 million years ago, not from a single process, but from ancient rivers depositing rounded quartz pebbles in their channels. These pebbles, cemented together with sand and smaller particles, created the conglomerate, literally stones within stone, visible in the cliff face as smooth, rounded shapes embedded in the matrix. Each pebble was rolled downstream by some Pennsylvanian river, worn smooth by tumbling through rapids and over bars, only to be buried and transformed into permanent rock. Now, water falls over these ancient river deposits, creating a kind of temporal loop, modern water flowing over the fossilized remains of ancient water's work. The falls have cut a small gorge through the conglomerate, retreating upstream gradually as the falling water undermines the rock face. In winter, the falls freeze into complex ice formations, the cascade transformed into blue-white sculpture that grows throughout the cold months. Blue Hen Falls hides in a narrow side gorge less than 2 miles from Brandywine, a smaller and more intimate waterfall that drops just 15 feet but flows year-round with remarkable consistency. While many Ohio waterfalls dwindle to trickles during dry summers, Blue Hen maintains its flow because it's fed primarily by springs rather than by surface runoff. Underground water emerges from cracks in the bedrock, having filtered through porous sandstone layers that act as natural aquifers. This spring-fed nature gives the water clarity and constant temperature, creating habitat conditions that remain stable even when the surface world experiences drought or flood. The narrow gorge amplifies the sound of falling water, creating an acoustic environment that feels separate from the broader landscape. Moss grows thick on the shaded rock faces, and ferns root in crevices where they catch the waterfall's mist. The scale is human rather than monumental. You can stand close enough to feel the spray, close enough to see individual water droplets separating from the main flow. Such intimate waterfalls invite contemplation rather than awe, offering gentle presence rather than overwhelming spectacle. The falls will be here tomorrow, next year, next century, fed by the patient movement of groundwater through stone. The Ohio and Erie Canal once threaded 309 miles of artificial waterway from Cleveland on Lake Erie to Portsmouth on the Ohio River, an engineering achievement that transformed Ohio's economy and settlement patterns in the decades before railroads rendered it obsolete. The canal required 146 lift locks to navigate the 206-foot elevation change between the two endpoints, essentially creating a staircase of water through which boats could climb and descend the landscape. Each lock represented a small triumph of engineering. Stone chambers where water levels could be raised or lowered by opening and closing gates, lifting or lowering boats by 10 or 15 feet at a time. The locks had to be precisely built, their walls mortared tight enough to hold pressure, their gates fitted carefully enough to prevent excessive leakage. The canal followed valleys where possible, but where ridges intervened, engineers excavated deep cuts through the bedrock. In other places, they built the channel atop earthen embankments, creating artificial rivers suspended above the natural terrain. The entire system took decades to complete and operated for only a few decades before trains offered faster, more flexible transportation. Today, remnants of the canal remain, dry sections where the towpath still exists, restored locks that demonstrate the system's operation, and occasionally stretches where water still flows in what was once the busy commercial highway of early Ohio. Ohio's Continental Divide runs roughly northeast to southwest through the center of the state, an invisible line that determines the ultimate destination of every raindrop that falls. Water landing north and east of this divide flows toward Lake Erie and the St. Lawrence River, eventually reaching the Atlantic Ocean. Water falling south and west flows to the Ohio River and the Mississippi system, ultimately reaching the Gulf of Mexico. This divide doesn't follow a mountain ridge as continental divides often do. Instead, it meanders across relatively flat terrain, where the elevation changes are so subtle that standing on the divide itself provides no visual clue to its significance. The divide's location was determined by glacial deposits that blocked pre-existing drainage patterns, forcing water to find new routes to the sea. In some places, the divide runs through active farmland. In others, it passes through suburban developments where homeowners might never know their front yard drains to the Atlantic, while their backyard drains to the Gulf. This imperceptible line has profound implications for watersheds and ecosystems, separating fish populations and aquatic communities as effectively as a mountain range, yet doing so with no obvious physical barrier to mark its presence. A farm field near Williamsport straddles the Continental Divide so precisely that a single rainstorm sends water in fundamentally different directions depending on which furrow catches it. Rain falling on the field's western half begins a journey of thousands of miles southward and westward, flowing to the Scioto River, then the Ohio, then the Mississippi, finally reaching the Gulf of Mexico and the warm waters of the Caribbean. Rain falling on the eastern half flows northward to the Olentangy River, then the Scioto, but then diverges to the Maumee River system, reaching Lake Erie, passing through the St. Lawrence River, and ultimately flowing into the Atlantic's cold northern waters. The distance between these two fates might be measured in tens of feet across a plowed field where the elevation change is invisible to the eye. Think about the separate paths those water molecules take. The time required differs vastly. The Gulf-bound water completes its journey in weeks or months, while the Atlantic-bound water might spend years circulating through the Great Lakes before continuing to the ocean. This division happens silently, invisibly, determined by subtle topography shaped by glaciers that melted 18,000 years ago. The farmer working this field probably knows about the divide, though it affects the crops not at all. Corn grows equally well, whether its roots draw water destined for the Gulf or the Atlantic. The Great Black Swamp once spread across approximately 1,500 square miles of northwestern Ohio, creating an impenetrable wetland that defied easy settlement and slowed westward expansion for decades. This wasn't a single body of open water, but rather a vast region of saturated ground, standing water, dense forest growing from soggy soil, and channels that changed course with seasons and floods. the swamp formed because the land here is so flat that water couldn't drain efficiently. Glacial deposits had blocked the natural drainage patterns, creating a massive region where water accumulated with nowhere to go. The forest that grew in these conditions was dark, dense, mosquito-infested, and hostile to travel. Roads became impassable in wet weather. Disease flourished in the stagnant waters. Early settlers attempting to cross the swamp described it with a mixture of awe and horror, a landscape that refused to be tamed, that swallowed efforts to establish roads and settlements. Draining the Great Black Swamp became a multi-generational project, requiring extensive networks of drainage tiles, ditches, and canals. By the early 20th century, most of the swamp had been converted to farmland, its rich organic soils proving extraordinarily productive once the water was removed. What was once considered worthless became some of Ohio's most valuable agricultural land. Only fragments of the Great Black Swamp remain today, protected in scattered preserves that offer glimpses of what once dominated northwestern Ohio's landscape. Gall Woods State Nature Preserve protects one of the best remaining examples, where ancient forest still grows from perpetually moist soil and water pools among massive bur oak and swamp white oak trees. Some of these trees are 500 years old, survivors of both the logging era and the agricultural transformation that claimed most of their companions. Walking through Gall Woods in spring when the water is high requires careful navigation, stepping from slight rises to fallen logs to patches of relatively dry ground. The forest floor is a maze of pools and puddles, reflecting sky between the dark tree trunks. Mosquitoes still swarm here in summer, and the air carries the rich smell of decay and growth happening simultaneously. This is what the Great Black Swamp was, not spectacular in the way of mountains or canyons, but powerful in its resistance to human purposes, its insistence on remaining wet, despite our preference for dry. The trees here grow slowly in the difficult conditions, their wood dense and hard, their roots adapted to standing in water for months at a time. They represent persistence, both their own and the swamp's. The Oak Openings region near Toledo contains an ecosystem so botanically diverse that it supports more than 1,000 plant species, including 85 found nowhere else in Ohio. This diversity emerges from the region's unusual substrate, sand dunes deposited by glacial lake waters that created soil conditions completely different from the clay-rich till covering most of northern Ohio. The sandy soil drains rapidly, creating dry conditions, despite the region's proximity to Lake Erie. This drainage, combined with the sand's low nutrient content, favors plants adapted to difficult conditions. Oak trees grow here in a savanna-like setting, widely spaced with grassy understory replacing the dense forest typical of Ohio. The openness gives the region its name, though fire suppression has allowed the forest to become denser than it was historically. Rare plants find refuge here because the sandy soil limits competition from more aggressive species that dominate clay soils. Lupines bloom in spring, their purple flower spikes adding color to the sandy expanses. Prickly pear cactus grows here despite the northern latitude, thriving in the well-drained sandy soil that mimics desert conditions. The region functions as a botanical island, supporting species that have no other Ohio habitat, their populations isolated in these sandy patches like oceanic islands scattered across a sea of clay till. These inland sand dunes near Toledo rise up to 25 feet high and shift subtly over decades, their sand having been deposited as beach material by ancient Lake Warren, which once covered this region when it stood 5 times larger than modern Lake Erie. As the glacial ice melted and retreated northward, massive volumes of meltwater pooled against the ice front, creating temporary lakes that expanded and contracted as ice conditions changed. Lake Warren represented one stage in this succession of prehistoric Great Lakes, its shoreline marking a temporary equilibrium between ice, water, and land. The lake's waves worked the shoreline just as modern Lake Erie's waves do, sorting sand particles and building beaches and dunes along its margins. When the lake level dropped as ice retreated further and allowed new drainage routes to open, the dunes were left high and dry, miles inland from the much-reduced Lake Erie. Wind continues to move the sand grain by grain, especially where vegetation hasn't fully stabilized the dunes. After severe storms or disturbances that remove vegetation, you can sometimes see the dunes migrate slowly, sand particles rolling up the windward side and cascading down the leeward slope. These are young landforms by geological standards, their sand only 14,000 years removed from being beach deposits, their shapes still responding to wind and weather. Glacial Lake Maumee represents the immediate predecessor to modern Lake Erie, though it was a dramatically different body of water, deeper, larger, and existing only briefly in geological terms. At its maximum extent, Lake Maumee stood roughly 760 feet above current sea level, making it nearly 190 feet deeper than today's Lake Erie, and covering far more territory across northern Ohio, Indiana, and Michigan. The lake formed when retreating ice left a depression but still blocked the St. Lawrence drainage route, forcing meltwater to pool against the ice front. As the ice continued retreating, the lake's level and extent changed repeatedly, sometimes dramatically. New outlets would open, draining the lake rapidly to a lower level. Ice would re-advance, blocking outlets and allowing water to rise again. This dynamic instability meant Lake Maumee existed more as a series of related lakes at different levels rather than as a single stable body of water. Each level left its mark on the landscape in the form of beach ridges, wave-cut terraces, and deltaic deposits. These features remained after the lake drained, creating subtle topographic variations that influenced where settlers built towns, where roads were established, and how agriculture developed. Modern Lake Erie occupies only the deepest portion of the basin that once held Lake Maumee's much greater volume. Ancient beach ridges from these prehistoric glacial lakes still stripe the landscape near Oak Harbor and Fremont, creating subtle parallel lines that are barely perceptible at ground level, but clearly visible in aerial photographs and topographic maps. Each ridge represents a pause in the dropping lake levels, a time when waves worked a particular elevation long enough to build a recognizable deposit of sand and gravel. The ridges run roughly parallel to modern Lake Erie's shoreline, though they may lie miles inland. Between the ridges, lower areas mark the lake bottom elevations, now drained but still reflecting their underwater origins in their flatter topography and different soils. Early settlers recognized these ridges as dry ground suitable for building, and many towns in northwestern Ohio sit along ancient beach ridges that provided natural elevated routes through otherwise swampy terrain. The ridges themselves are rarely more than 10 or 15 feet higher than surrounding land, but even this modest elevation made enormous difference in drainage and accessibility. Highway 2 along Lake Erie's southern shore follows ancient beach ridges for much of its route, taking advantage of the same elevated dry ground that attracted the first human inhabitants thousands of years ago. These ridges are invisible monuments to vanished lakes, their gentle curves recording shorelines that existed when mastodons still grazed northern Ohio's tundra-like vegetation. Ohio Caverns near West Liberty features the Crystal King, a stalactite formation 5 feet long that hangs like a pendant of pure calcite, its crystalline structure so precise that light passes through it with barely any distortion. The formation is estimated to be over 400,000 years old, growing at the almost imperceptible rate typical of cave formations in temperate climates. Each molecule of calcite added to the Crystal King arrived in solution, dissolved in water that seeped through the limestone above, then precipitated out when that water encountered the cave's air and released its dissolved carbon dioxide. The process continues today at the same patient pace, adding perhaps 1 cubic inch of new calcite every century. The Crystal King's nearly transparent appearance comes from the purity of the formation. Few impurities have been incorporated into its structure, allowing it to form nearly perfect calcite crystals. Under specialized lighting, the formation seems to glow from within, though what you're seeing is light passing through the calcite rather than any luminescence. The formation hangs in a chamber where air circulation is minimal, preventing dust accumulation that would cloud its surface. Standing before the Crystal King, you're looking at 400 millennia of mineral deposition, one water drop at a time, one molecule at a time, building slowly toward a structure that will outlast human civilization. The caverns maintain a constant 54 degrees Fahrenheit throughout the year, with humidity near 100%, creating conditions that never vary regardless of surface weather. In summer, entering the caverns means stepping into suddenly cool air that raises goosebumps on your skin. In winter, the caverns feel almost warm by comparison to the frozen landscape above. This thermal stability exists because limestone is an excellent thermal buffer. The rock temperature equilibrates to the average annual surface temperature, and the mass of stone surrounding the caverns is so enormous that daily or seasonal temperature variations at the surface never penetrate to the cave level. The constant conditions are critical for formation growth. Stalactites, stalagmites, and other speleothems form through delicate chemical processes that depend on relatively stable temperature and humidity. Dramatic variations would disrupt these processes. The near-perfect humidity means water in the caverns never fully evaporates. Instead, it moves through cycles of seeping, dripping, and flowing, always remaining liquid, always carrying dissolved minerals, always contributing to the slow growth of formations. The rate of 1 cubic inch per century might seem frustratingly slow from a human perspective, but given geological time, even this pace builds substantial structures. The Crystal King's 5-foot length represents consistent growth over nearly 500,000 years, a span that dwarfs all of human history. Seneca Caverns near Bellevue descends 7 stories underground through a vertical crack in the limestone, the passages growing narrower and more confined as you go deeper. The cavern system formed when an ancient earthquake fractured the bedrock, creating a vertical fissure that water could exploit. Over millennia, slightly acidic groundwater dissolved the limestone along this crack, widening it from a hairline fracture to passages large enough to permit human access. But the vertical nature of the main passage makes this cave unusual among Ohio's cavern systems. You don't walk horizontally through chambers. Instead, you descend, sometimes on stairs, sometimes on ladders, always moving deeper into the bedrock. In places, the walls close in until you must turn sideways to continue, your shoulders brushing limestone on both sides. The sense of enclosure intensifies as you descend, the weight of stone above you becoming palpable in a way it rarely feels in horizontal caves. The air is damp and cool, carrying the smell of limestone and stagnant water. Dripping sounds echo from various depths, creating an acoustic environment that makes it difficult to judge distances. The deepest accessible level lies more than 100 feet below the surface, where the temperature and darkness remain absolutely constant. This is the limestone's interior, the heart of the bedrock, rarely seen and largely unchanged since the crack first opened in some long-forgotten seismic event. At the bottom of Seneca Caverns flows Ol Mystery River, an underground stream whose source and destination remain genuinely unknown despite decades of investigation. The river emerges from one crack in the limestone and disappears into another, flowing through the deepest accessible chamber with water clear enough to see the limestone bottom. Where does the water come from? No one knows with certainty. Researchers have poured dye into sinkholes and losing streams for miles around, hoping to see it emerge in Ol Mystery River and thus prove the connection. The dye never appears. Where does the water go? That's equally mysterious. More dye has been introduced to the underground river itself. Then researchers have watched springs and streams throughout the region, waiting for the telltale color to appear. It doesn't. The river simply vanishes into the limestone labyrinth, following passages too small or too flooded for human exploration. The flow rate varies with rainfall, proving the river connects to the surface water system somehow, but the specific connections remain hidden. This mystery has persisted so long, it's become part of the cavern's identity. Ol Mystery River lives up to its name, flowing through darkness from unknown origin to unknown destination, indifferent to our curiosity about its secrets. The Olentangy Caverns near Delaware feature a massive underground chamber 55 feet wide with a limestone ceiling arching overhead like a natural cathedral. Local legend claims Confederate soldiers hid in this chamber during the Civil War, using the caverns to escape Union authorities, though historical evidence for this claim is scarce and disputed. The legend persists partly because it feels plausible. The caverns certainly could have sheltered refugees, deserters, or escaped prisoners. The chamber is large enough, remote enough, and difficult enough to access that it might have served this purpose. But the absence of documentation, the vagueness of the stories, and the tendency for caves everywhere to accumulate similar legends make historians skeptical. What's certain is that the caverns have sheltered humans intermittently for thousands of years. Archaeological evidence shows indigenous use of the entrance areas. Early European settlers knew about the caverns and likely explored them by torchlight. The chambers formed through the same slow dissolution process that creates all limestone caves, slightly acidic water seeping through cracks, gradually widening them into passages and rooms. The 55-foot chamber represents hundreds of thousands of years of dissolution, the ceiling held up by the inherent strength of the limestone arch. The rock above is under compression, held in place by its own weight and shape, creating a stable structure that will stand for many more millennia. Zane Caverns in Logan County contains helictite formations that seem to defy every reasonable expectation about how stalactites should grow. Normal stalactites hang straight down, following gravity as water drips from their tips. Helictites twist and curve in seemingly impossible directions, extending horizontally from walls, spiraling upward against gravity, branching at odd angles that make no visual sense. These peculiar formations grow through capillary action rather than simple dripping. Water moves through tiny channels within the calcite crystal structure, emerging at the tip and depositing new calcite in directions determined by the crystal's internal geometry, rather than by gravity. The result is formations that look more like frozen tentacles or white coral than like typical cave features. Some helictites are delicate and fragile, barely thicker than a pencil, extending a foot or more from their attachment point with nothing but their own crystalline structure providing support. Others branch repeatedly, creating bush-like masses of twisted calcite. The formations grow even more slowly than normal stalactites because the water movement through capillary action is slower than simple dripping. A helictite might grow only a fraction of an inch per 1,000 years. Their rarity and delicate nature make them prized features in caves that contain them. They're easily destroyed by touch or vibration, representing geological patience that can be undone by a moment's carelessness. The Hinckley Reservation hosts one of nature's most punctual events each spring, as turkey vultures return from their southern wintering grounds to cliff faces along the Rocky River Valley, with remarkable consistency, typically appearing on or near March 15th each year. Locals have been observing and celebrating this return for generations, creating a tradition that parallels the famous return of swallows to San Juan Capistrano. The vultures migrate north from their winter range in the southern United States, arriving in Hinckley when conditions allow them to find sufficient carrion to sustain themselves. Their timing isn't magical or mystical, but rather reflects the birds' sensitivity to seasonal changes and their remarkable navigational abilities. The same cliffs and thermal updrafts that attracted vultures centuries ago continue to attract them today. The birds aren't individually loyal to Hinckley. A particular vulture might roost elsewhere, but the population as a whole returns to the same general area year after year, generation after generation. Hundreds of birds spiral on rising air currents above the reservation. Their wings spread wide in a characteristic dihedral shape, rarely flapping, instead riding invisible columns of heated air that allow them to soar for hours while expending minimal energy. The return marks spring's arrival as surely as any flowering plant or migrating songbird, a sign that winter's grip is loosening and life is returning to the northern landscape. These Hinckley buzzards, as locals affectionately call them, roost on cliffs of Berea sandstone that rise nearly 200 feet above the Rocky River Valley. The stone's age estimated at 350 million years. The cliffs formed not through uplift, but through erosion. The river has cut downward over thousands of years, carving through the sandstone and creating vertical walls. The Berea sandstone is resistant to erosion compared to softer shales below it, so it forms the caprock, the layer that creates the cliffs. The cliff faces provide ideal roosting sites for vultures, offering protection from ground predators, excellent visibility, and immediate access to the updrafts that form along the valley walls as sun-heated air rises. From their roosts, the vultures can see for miles across the landscape, spotting potential food sources with eyesight far sharper than human vision. The sandstone itself began as beach sand 350 million years ago, when this region lay near the shore of a shallow sea. Those sand grains were deposited, buried, compressed, and cemented into solid rock, then exposed again by erosion. Now they serve as foundation for turkey vultures that have no concept of the stone's ancient origins, that care only that the cliffs provide what they need: height, shelter, and access to the invisible rivers of air that make their soaring flight possible. The Berea sandstone underlies much of northern Ohio, sometimes exposed at the surface in quarries and stream valleys, other times buried beneath younger glacial deposits. The formation extends in a broad band across the state, its depth varying from surface outcroppings to several hundred feet below ground. This particular sandstone gained fame not for its appearance, but for its function. The rock's uniform, medium grain texture made it ideal for grinding and sharpening, and for more than a century, Berea sandstone grindstones were considered the finest available anywhere. The uniformity matters because grinding requires consistent abrasion. If some areas of the stone are harder or softer, the grinding surface becomes uneven, reducing effectiveness. Berea sandstone maintains remarkable consistency throughout individual beds, meaning a grindstone quarried from this formation would wear evenly, keeping its shape through years of use. The sand grains that became this rock were deposited in a near-shore marine environment approximately 350 million years ago. The waves and currents sorted the sand, removing larger pebbles and finer silts, leaving behind grains of nearly identical size. This natural sorting, happening grain by grain over centuries of deposition, created the uniformity that would make the stone valuable hundreds of millions of years later. The sandstone's value demonstrates how geological processes with no human purpose can nevertheless create exactly what humans later need. At Berea's quarries in the 1800s, workers carved massive circular grindstones that weighed several tons, each one cut painstakingly from the bedrock and shaped with precision tools. The work was slow and demanding. A single large grindstone might take weeks to produce, requiring careful measurement to ensure perfect roundness and uniform thickness. The stones were shipped worldwide, sent by canal and later by rail to workshops, factories, and mills across North America and Europe. Berea became synonymous with quality grinding implements, from small knife-sharpening stones to industrial-sized wheels used in manufacturing. Some grindstones measured 6 feet in diameter or more, their weight requiring specialized equipment to move and mount. Despite their mass, they would eventually wear away completely through use, the sandstone abraded particle by particle until nothing remained but the memory of their service. The quarries that produced them have mostly closed now, their commercial importance diminished by synthetic abrasives that can be manufactured to exact specifications. But the stone itself remains, exposed in cuts and outcrops, still uniform in texture, still capable of sharpening a blade, still bearing the properties that made it valuable. The difference is that now we have other options, and the sandstone can simply be stone, appreciated for itself rather than for what it can do. Clifton Gorge near Yellow Springs cuts 100 feet deep through Silurian dolomite, exposing rock layers 430 million years old in vertical walls that confine the Little Miami River to a narrow channel. The gorge formed through erosion, the river exploiting weaknesses in the bedrock, cracks, joints, areas where the rock was slightly softer or more fractured. Over thousands of years, the water worked these weaknesses, widening them, deepening them, eventually creating a chasm where Gentle Creek had once meandered across a broader valley. The process continues today at an imperceptible pace. Each flood carries abrasive sand and pebbles through the gorge, scouring the bedrock. Each freeze-thaw cycle in winter cracks the rock a little more, loosening fragments that the next high water will carry away. The dolomite itself formed in a shallow tropical sea, its calcium and magnesium carbonates precipitated from the warm water or accumulated as shell fragments from marine organisms. The rock bears evidence of this origin in its fossil content and its bedding patterns. Now it stands in vertical walls above a fast-flowing river in a decidedly non-tropical climate. Its orientation changed from horizontal to vertical by millions of years of erosion. Its appearance transformed from seafloor to gorge wall through processes that never cease working. The Little Miami River flows 111 miles from headwaters near Springfield to its confluence with the Ohio River, draining approximately 1,700 square miles of southwestern Ohio. The river earned designation as a National Scenic River, recognition of its relatively undeveloped character and its value for recreation and wildlife habitat. Unlike many Ohio rivers that were extensively modified for navigation or flood control, the Little Miami retains much of its natural character, its course winding through forested valleys with minimal channelization. The designation protects the river from certain types of development and ensures that its scenic qualities will be preserved for future generations. The river's flow varies dramatically with seasons and rainfall, ranging from shallow riffles in late summer to powerful floods in spring. This variation creates diverse habitat conditions, supporting fish species adapted to different flow regimes. Smallmouth bass thrive in the faster water sections. Catfish prefer deeper pools. The river corridor provides migration routes for songbirds and habitat for mammals from muskrats to river otters. The Little Miami's name distinguishes it from the Great Miami River to the west, though the two rivers share no connection beyond their names, which derive from Native American words, filtered through European pronunciation and spelling that obscured their original meanings. Glen Helen Nature Preserve surrounds the Yellow Spring, for which the adjacent town was named, a natural spring that flows with water tinted distinctly yellow by dissolved iron oxides. The spring emerges from dolomite bedrock at a rate of roughly 100 gallons per minute, maintaining consistent flow year-round, regardless of drought or deluge. The yellow color comes from iron present in the bedrock through which the water passes. As groundwater seeps through the rock, it dissolves small amounts of iron. When this iron-rich water emerges into the air and encounters oxygen, the iron oxidizes, creating yellow and orange precipitates that tint the water and coat the rocks near the spring. The coloration is purely mineral, not biological, though iron oxidizing bacteria may contribute to the process. Native Americans knew this spring and likely attributed significance to its unusual color. Early European settlers were struck by it as well, giving both spring and town their names based on this distinctive feature. The water itself is potable, the iron content well within safe levels, though it tastes distinctly metallic. The spring feeds a small stream that flows through Glen Helen, its yellow-tinted water visible against the gray dolomite bedrock. In certain lights, the water seems almost luminous, as though the yellow color comes from within rather than from suspended particles. The spring will continue flowing as long as the aquifer feeding it remains charged with groundwater seeping down from the surface above. The Glacial Grooves State Memorial on Kelly's Island protects only a fraction of the original grooves that once covered much larger areas of exposed limestone. In the late 1800s, before the grooves' scientific value was fully recognized, quarrying operations destroyed the majority of these spectacular geological features. The limestone itself was valuable for construction, and quarry operators saw bedrock to be extracted rather than phenomena to be preserved. Thousands of tons of grooved limestone were removed, cut into blocks, and shipped away to build foundations and facades in cities across the region. By the time preservation efforts began, only a small area of grooves remained intact. What survives is remarkable enough. Some of the world's finest examples of glacial striations, clear and deep and extensive, but the original display must have been even more impressive, covering acres rather than the small preserved area that remains. This pattern repeats throughout Ohio's geological heritage. Many significant features were destroyed or severely damaged before their importance was understood. The Black Hand petroglyph was mostly destroyed by canal construction. Numerous waterfalls were harnessed for mill power, their character changed by dams and diversions. Ancient earthworks were plowed under or built over. We preserve what remains, but we can only imagine what was lost, what future generations will never see, because preservation came too late to save it. Inscription. Rock on Kelly's Island displays more than 50 petroglyphs carved into exposed limestone by Erie people between 1200 and 1600 CE. The carvings depict stylized human figures, animals, and geometric designs whose full meaning remains uncertain. Some appear to be pictographic, representing specific beings or events. Others might be symbolic, conveying concepts rather than concrete images. The rock is large, a glacially smoothed limestone surface near the island's southern shore, and the carvings cover much of its expanse. Unfortunately, both natural weathering and human vandalism have made many images difficult to distinguish. Wind and rain slowly erode the limestone, softening the carved lines. Freeze-thaw cycles in winter crack the surface. But worse than natural weathering has been deliberate damage, names and initials scratched by visitors over the centuries, obscuring original carvings. Modern preservation efforts try to prevent further damage, but cannot reverse what's already occurred. What remains gives us tantalizing glimpses into the artistic and cultural expressions of people who lived here centuries ago. They chose this particular rock for reasons we can only guess. Perhaps its smooth surface, perhaps its prominent location, perhaps some significance that isn't apparent to modern observers. They carved these images with stone or bone tools, working the hard limestone with patience and skill. The result was meant to last, to communicate across time. And indeed it has, though imperfectly, the message degraded but not entirely lost. The Maumee River stretches 137 miles from its formation at the confluence of the Auglaize and St. Mary's rivers to its mouth at Lake Erie, making it the largest river flowing into the Great Lakes by volume. The river drains 6,600 square miles of northwestern Ohio and northeastern Indiana, gathering water from a vast network of tributaries that spread across the flattest portions of both states. This flat terrain means the river's gradient is exceptionally gentle, dropping only about 200 feet over its entire length. The sluggish current allows sediment to settle, and the Maumee carries enormous loads of suspended material, especially during spring floods. This sediment built the delta lands around Toledo, extending the shoreline gradually into Lake Erie. The river's mouth is constantly changing as currents deposit sediment in some areas and erode it from others. The Maumee's watershed encompasses much of the former Great Black Swamp, that vast wetland that was drained for agriculture. Now the river carries not just natural sediment, but also agricultural runoff, nutrients from fertilized fields that contribute to algal blooms in Lake Erie's western basin. The river that once flowed through wilderness now flows through one of America's most intensively farmed regions, its water quality reflecting every choice made across 6,600 square miles of cropland. During spring floods, the Maumee can discharge 130,000 cubic feet of water per second, a volume difficult to comprehend until you see it, the river transforming from a modest stream to a roiling brown torrent that spreads beyond its banks into the floodplain. Summer flows, by contrast, might drop to barely 1,000 cubic feet per second, a dramatic 130-fold variation that reflects the watershed's flat topography and the seasonal precipitation patterns of the Midwest. Rain and snow melt in spring have nowhere to go quickly in such flat terrain, so water accumulates, raising stream levels until the land is saturated and cannot absorb more. Then the water moves toward the river, arriving in pulses that can cause flooding weeks after the precipitation that caused it. In summer and fall, when rainfall decreases and evapotranspiration increases, the streams recede, sometimes dramatically. The Maumee in August might be crossable on foot in places, a far cry from the spring torrent. This variability affects everything in and around the river. Fish adapted to high flows struggle during low water. Boat traffic possible in spring becomes impossible in summer. The river's character changes so dramatically with the seasons that it seems like different rivers occupying the same channel. The Maumee Bay State Park beach stretches along Lake Erie on land that was underwater marsh just 8 decades ago, before extensive filling and engineering transformed swamp into sandy beach. The transformation required thousands of truckloads of sand and the construction of breakwaters to protect the new beach from erosion. What was once cattail marsh and shallow water became 2,000 feet of recreational beach, complete with swimming areas, facilities, and parking. The project demonstrates humanity's ability to reshape landscapes according to our preferences, to take land in one state and convert it to another purpose entirely. The marsh that existed here was part of the vast wetland complex that characterized Lake Erie's southern shore before development. These marshes were biologically productive, supporting enormous populations of fish, waterfowl, and other wildlife. But they were also seen as obstacles to recreation and economic development. The decision to fill marsh and create beach reflected mid-20th century attitudes toward wetlands, which were viewed as wastelands to be reclaimed rather than as valuable ecosystems to be protected. Today, environmental regulations would make such a project difficult or impossible to permit. We've learned that wetlands provide critical functions, filtering water, providing habitat, buffering against floods. But the beach remains, an artifact of different priorities, serving millions of visitors who may never know they're recreating on land that was recently swamp. The Hocking River Valley contains more than 25 significant waterfalls within a 25-mile radius, creating one of the highest concentrations of waterfalls in the eastern United States outside the Appalachian Highlands. This concentration results from the valley's unique geology. Layers of resistant sandstone caprock overlying softer shales that erode more readily. Water flowing over the sandstone eventually undermines the softer rock below, causing the sandstone to break away in blocks, creating and maintaining the vertical drops. The falls are scattered throughout the valley at different elevations, fed by different streams, each with its own character and flow patterns. Some, like Ash Cave Falls, are tall and delicate. Others, like Cedar Falls, are broader and more powerful. The variety comes from differences in the bedrock layers, in stream size, in the particular geometry of each location. The concentration of falls in such a relatively small area makes the Hocking region unusual. Most landscapes might have 1 or 2 significant waterfalls in an area this size. The Hocking has dozens. This abundance reflects not just the geology, but also the region's relief. Enough elevation change to create drops, but not so much that streams become torrents. The result is a landscape punctuated by falling water, a region where the sound of cascades is never far away. Cedar Falls drops 50 feet into a plunge pool, carved into Blackhand sandstone, its water fed by Queer Creek, which flows year-round thanks to groundwater seeping through porous rock layers upstream. The falls are among the most visited in the Hocking region, accessible via a moderate trail that winds through hemlock forest to reach the viewing area. The Kui sandstone behind the falls is undercut, creating a shallow recess where you can stand behind the falling water during low flows. The experience of standing in this space is peculiar, half in shadow, half in the mist created by the falling water, surrounded by the sound of the cascade. The walls are damp, supporting moss and ferns that thrive in the constant moisture. The plunge pool is surprisingly deep, 20 feet or more in places, carved by thousands of years of falling water abrading the bedrock. Sediment that settles in the pool during calm periods gets scoured out during floods, maintaining the pool's depth. The pool's water is cold even in summer, fresh from underground springs, and clear enough to see bottom in the shallows. The fall's consistency makes them reliable. Visit in July or January, after drought or during floods, and water will be falling. The volume changes, sometimes dramatically, but the falls themselves persist, fed by that steady groundwater flow that finds its way to the surface here, regardless of surface conditions. Cantwell Cliffs presents a narrow, winding quarter-mile rim trail perched atop sandstone cliffs, rising 150 feet above the valley floor. The path carved between vertical walls with overhangs, creating shallow recesses called rock houses. Walking this trail requires attention. The passage is sometimes just a few feet wide, with cliff edge on one side and rock wall on the other. In places, the overhang extends so far that you're essentially walking through a shallow cave open on one side to the valley below. These rock houses provided shelter for indigenous peoples and later for settlers and travelers. The recesses are dry, protected from rain by the overhanging sandstone, and relatively warm in winter as the rock moderates temperature extremes. The formation of these features follows a pattern common in the Hocking region. The Black Hand sandstone forms a resistant caprock. Below it lie softer shales that erode more easily. As the shales weather away, they undercut the sandstone, which then breaks away along vertical joints, creating the cliffs. But before breaking away completely, the sandstone sometimes remains as an overhang, cantilevered over empty space, held up by its own strength until eventually, it too collapses. The rock houses represent this intermediate stage, overhangs that haven't yet fallen, but will eventually. Standing beneath these overhangs, you're sheltered by stone under tension, rock-defying gravity through internal structure, temporary in geological terms, but seemingly permanent in human ones. The rock house stands as Ohio's only true cave, a tunnel-like formation 200 feet long, 25 feet high, and 75 feet deep, carved entirely within a single massive cliff of Middle Black Hand sandstone. Unlike the state's many limestone caverns, which are solution caves formed by dissolving rock, the rock house is an erosional feature created by water, wind, and freeze-thaw cycles working on the sandstone. The formation occupies a single thick layer of sandstone, a lens-shaped body within the larger formation. Water seeping into this layer found it more porous than surrounding rock, so it flowed through the layer preferentially, slowly removing sand grains and cement, gradually hollowing out the interior. The process took hundreds of thousands of years, working from weaknesses and cracks, expanding them into passages until the hollow space grew large enough to be called a cave. The rock house ceiling is arched, distributing weight efficiently so the structure remains stable despite the hollow interior. The floor is sandy, composed of material that's eroded from the walls and ceiling over millennia. The cave stays cool in summer and relatively warm in winter, its temperature moderated by the thermal mass of surrounding stone. This temperature stability made it attractive to people and animals seeking shelter throughout the centuries. 7 window-like openings pierce the rock house's front wall, natural portals formed where softer layers within the sandstone eroded faster than harder surrounding stone. These windows range from small gaps barely large enough to peer through to large openings several feet across. Each window frames a different view of the forest valley below, creating natural picture frames that change with the seasons: bare branches in winter, green canopy in summer, colorful foliage in fall. The windows formed through differential erosion, a common process in layered sedimentary rock. Even within a single sandstone formation, some layers contain more cement between grains, making them more resistant to weathering. Other layers are less well cemented, more porous, more vulnerable to erosion. As water and air work the rock face, these softer layers erode preferentially, eventually creating holes completely through the wall. The process continues today. The windows are slowly growing larger as erosion removes more material from their edges. In geological time, the windows will eventually merge and the front wall will collapse, transforming the rock house from a cave into an overhang, then eventually into nothing as the entire formation weathers away. But that transformation will take tens of thousands of years, and for now, the rock house remains intact, its windows providing light and air to the interior. Conkle's Hollow State Nature Preserve protects Ohio's deepest gorge, where 200-foot cliffs rise vertically from a valley floor, barely 300 feet wide at the narrowest point. The gorge creates a landscape of verticality unusual in Ohio, where most topography is measured in tens of feet rather than hundreds. The cliffs are blackhand sandstone, the same resistant formation that creates so many features in the Hawking region. The gorge formed through erosion along a geological weakness, probably a fault or joint in the bedrock that allowed water to concentrate its cutting action. Once the stream established its course, it cut downward faster than it could cut sideways, creating the narrow, deep profile. The gorge walls are nearly vertical in places, with overhangs where the sandstone has been undercut. Rockfall is common here. Look at the valley floor and you'll see massive sandstone blocks that fell from the walls above, their edges still sharp, their fall recent in geological terms. Eventually, these blocks will be broken down by weathering and carried away by floods, making room for the next fall. The process of gorge formation continues, but at a pace so slow that generations of human visitors will notice no change. The cliffs stand as they have for millennia, their height and steepness creating a landscape that feels more like the Western Canyonlands than like typical Ohio topography. The gorge at Conkle's Hollow maintains a microclimate significantly cooler and moister than the surrounding plateau, supporting Canada yew and other northern plant species typically found hundreds of miles north of Ohio. The deep shade created by the high walls reduces temperature and evaporation. Cold air, being denser than warm air, settles into the gorge bottom and remains there, creating a natural refrigerator. Water seeps from the sandstone walls throughout the year, keeping humidity high and providing moisture even during droughts. These conditions approximate the climate of northern Michigan or Wisconsin, allowing species adapted to northern conditions to survive here as relict populations, remnants of the cooler climate that prevailed across Ohio immediately after the glaciers retreated. As the climate warmed, these northern species retreated northward across most of their range, but in places like Conkle's Hollow, the microclimate allowed them to persist as isolated populations far south of their main range. The Canada yew found here may have been growing in this gorge continuously for 10,000 years or more, descendants of plants that colonized Ohio when the ice had just melted. These gorge populations serve as genetic time capsules, preserving lineages that may differ subtly from their northern relatives after millennia of separation. The cool, moist microclimate also supports exceptional moss and fern diversity, with species covering the lower cliff faces in a tapestry of green. Hayden Falls drops 35 feet over a ledge of Columbus limestone in a small park completely surrounded by suburban development in Dublin, an unexpected natural feature within sight of office buildings and shopping centers. The contrast is jarring. Stand at the falls and you're in what feels like wilderness. The sound of falling water, the cool mist, the limestone walls draped with moss. Turn around and you see the buildings of modern suburbia just hundreds of feet away. The falls survived development, partly by accident, and partly through preservation efforts by people who recognized their value. The stream feeding the falls, a small tributary of the Scioto River, was already in a steep-sided ravine, making the land less suitable for building. This accident of topography protected the falls until preservation became possible. Now the small park serves as a natural oasis in an otherwise heavily developed landscape. The falls flow year-round, though volume varies dramatically with rainfall. After storms, the water thunders over the ledge with enough force to create a cloud of mist that drifts through the ravine. During dry periods, the falls reduce to a modest flow, but they never completely stop, fed by groundwater seeping through the limestone. The existence of Hayden Falls demonstrates that nature persists even in urban settings, finding niches where conditions allow. The Ohio River forms 436 miles of Ohio's southern and eastern border, making it the longest continuous border feature of the state and the primary drainage route for 2/3 of Ohio's land area. The river flows southwest from its origin at the confluence of the Allegheny and Monongahela rivers at Pittsburgh, gathering water from tributaries throughout the Appalachian region and the Midwest before joining the Mississippi. For Ohio, the Ohio River represents both boundary and connection, a clear dividing line between Ohio and Kentucky, West Virginia, yet also a highway for commerce and communication that linked Ohio to larger river systems and ultimately to the Gulf of Mexico. Before railroads, the Ohio River was the primary route for moving goods and people westward. Flatboats, keelboats, and eventually steamboats carried settlers and cargo down the river, their journeys shaped by the river's current, sandbars, and seasonal flows. The river's level varies dramatically with rainfall in its vast watershed. Spring floods can raise water levels by 40 feet or more above low water marks, inundating bottomlands and occasionally threatening riverside towns. Low water in late summer can expose sandbars and rocks that make navigation treacherous. These variations are natural, though locks and dams built in the 20th century have moderated them somewhat, maintaining a navigation channel even during low water by creating a series of pools. The Ohio River remains one of the busiest commercial waterways in North America, its barges carrying coal, grain, petroleum, and manufactured goods in traffic that continues day and night throughout the year. At Marietta, the Muskingum River joins the Ohio after traveling 111 miles northward through a valley carved during glacial melt periods when massive water volumes sought any available outlet southward toward the Mississippi system. The Muskingum flows through what geologists call a meltwater channel, a valley carved not by the river that occupies it today, but by much larger flows of glacial meltwater. When the ice sheets were melting, the volume of water was enormous, far beyond what modern rivers carry. This meltwater needed to flow somewhere, and it followed the path of least resistance, cutting deep valleys in the process. When the ice finished melting and water volumes returned to normal levels, the rivers that remained were too small for the valleys they inherited. The Muskingum flows through a valley that seems oversized for it, carved for a much larger stream. The valley's width and depth provided easy routes for roads and railroads in later centuries, and numerous towns sprang up along its length. The confluence at Marietta marks the meeting of two significant river systems, with the Muskingum bringing water from the glaciated region of eastern Ohio and the Ohio, carrying water from across Appalachia. The combined flows proceed southwest toward the Mississippi, water molecules that fell as rain on the Alleghenies mixing with water that fell on Ohio's Till Plains, all of it moving together toward the Gulf of Mexico and the sea beyond. The Muskingum River watershed encompasses more than 8,000 square miles of southeastern Ohio, making it the largest tributary system entirely within the state's borders. This vast drainage area collects water from hundreds of smaller streams and creeks, channeling it all toward the Muskingum's main stem and ultimately to the Ohio River. The watershed includes portions of 26 counties, covering landscapes that range from the unglaciated Allegheny Plateau's rugged hills to gentler glaciated terrain in the northern reaches. Every raindrop falling within this 8,000 square mile area eventually flows through the same channel at Marietta before joining the Ohio. The concept of a watershed can seem abstract until you consider its implications. Stand anywhere within this enormous area, in a parking lot in Coshocton, a forest in Morgan County, a farm field near Zanesville, and watch rain fall. That water is beginning a journey that will carry it through tributaries and streams, into the Muskingum, then the Ohio, then the Mississippi, and finally to the Gulf of Mexico, potentially traveling 1,500 miles or more from where it fell. The watershed connects all these disparate places through the simple fact of water flowing downhill, gathering as it goes, combining into larger and larger streams until the individual raindrops become indistinguishable in the river's volume. Flint Ridge extends across parts of Licking and Muskingum counties, containing some of North America's highest quality flint deposits, quarried continuously by indigenous peoples for more than 13,000 years. The flint occurs in distinct layers within the bedrock, particularly in one bed called the Van Port Flint, which produces material prized for its workability and beauty. Flint is essentially a very fine-grained form of quartz, hard enough to hold a sharp edge, brittle enough to be shaped through careful fracturing. The ridge's flint comes in spectacular colors, reds, yellows, blues, purples, and combinations that can look almost like abstract paintings when the stone is fractured to reveal its interior. These colors result from trace impurities, primarily iron and manganese oxides, incorporated during the flint's formation in a shallow sea roughly 300 million years ago. The silica that became flint originally existed as dissolved minerals or as the remains of silica-secreting organisms like sponges. As these materials accumulated and concentrated, they formed nodules of flint within the limestone layers. Later erosion exposed these flint-bearing layers at Flint Ridge, creating one of the continent's premier sources of tool-making stone. Indigenous peoples recognized the quality of this flint and quarried it intensively, creating pits and trenches that are still visible today. Erosion-softened depressions where thousands of years of digging removed the valuable stone. The colorful flint from Flint Ridge, sometimes called Vanport Flint or Ohio Flint, appears in archaeological sites across eastern North America, having been traded as far as 1,000 miles from its source. Archaeologists have identified Flint Ridge flint, recognizable by its distinctive coloration and characteristics, in sites from the Great Lakes to the Gulf Coast, from the Atlantic to the Great Plains. This widespread distribution demonstrates extensive prehistoric trade networks that connected communities across vast distances. A spear point made from Flint Ridge flint and found in Wisconsin represents not just an artifact, but evidence of trade relationships, travel, and communication spanning hundreds of miles. The flint moved through these networks as a valuable commodity, probably traded hand-to-hand through chains of exchange rather than carried directly from source to final destination. The trade worked both ways. Materials from distant regions, including marine shells and copper from the Great Lakes, appear in Ohio archaeological sites, showing that Ohio peoples were participants in continent-wide exchange systems. The flint's journey from bedrock to blade to burial in distant soil represents one of the longest-lived trade relationships in human history, continuing for more than 100 centuries before European contact disrupted these traditional patterns. Ohio contains more than 70 identified prehistoric earthwork sites, second only to Mississippi in total number, with ceremonial and burial mounds dating from the Adena culture around 800 BCE through the Hopewell culture that flourished until approximately 400 CE. These earthworks range from small burial mounds to massive geometric enclosures covering hundreds of acres. The sheer number of sites demonstrates that Ohio supported substantial prehistoric populations with the organization and resources necessary to undertake major construction projects. Building these earthworks required moving thousands or sometimes millions of cubic yards of earth, all carried in baskets or animal hide containers, since wheeled vehicles and draft animals were unavailable. The labor investment was enormous, representing decades or generations of work involving hundreds or thousands of people. Many earthworks display sophisticated geometric precision and astronomical alignments, suggesting their builders possessed advanced surveying skills and celestial knowledge. The earthworks served various purposes: burial sites for important individuals, gathering places for ceremonies, astronomical observatories, territorial markers, or purposes we may not yet understand. Many were built in stages over long periods, with later generations adding to structures their ancestors began. The concentration of earthworks in Ohio reflects the region's advantages: rich soils supporting agriculture, abundant game, and access to major river systems that facilitated trade and communication. The Great Circle earthworks in Newark originally formed a perfect circle 1,200 feet in diameter, with walls 12 feet high, connected to an octagonal enclosure covering 50 acres. This represents some of the most precise geometric construction in prehistoric North America. Creating a circle this large with such accuracy using only simple tools and visual sighting required sophisticated surveying techniques. The builders likely used ropes or cords of standard lengths as measuring tools, stakes to mark positions, and careful observation to ensure the curve remained consistent. The resulting circle is accurate to within a few feet across its entire circumference, an achievement that impresses modern surveyors using advanced instruments. The octagonal enclosure connected to the circle through a short causeway, creating a unified complex whose purpose remains debated. Some researchers note astronomical alignments in the octagon's orientation, suggesting it functioned as an observatory for tracking lunar cycles. The walls themselves were built from earth excavated from interior areas and borrowed from nearby borrow pits, then shaped and compacted into substantial embankments. Much of the original complex has been destroyed by urban development. Newark grew up around, and eventually over many earthworks. What remains is protected, though surrounded by modern development that makes understanding the original landscape context difficult. Fort Ancient Earthworks near Lebanon encompasses 126 acres, with embankments stretching 3.5 miles around hilltop ridges. Though despite its name, it was never actually a fort, but rather a ceremonial site built between 100 BCE and 400 CE. The name reflects 19th century assumptions that such impressive constructions must have had military purposes, but archaeological evidence suggests ceremonial and astronomical functions instead. The earthworks follow the ridgetop's contours, creating an enclosure that would have been difficult to defend but spectacular for ceremonies that included large gatherings. The Embankments vary in height, reaching up to 20 feet in places, built from earth excavated from the interior and from external borrow pits. The construction followed the natural topography skillfully, using the hilltop's height to amplify the earthwork's visual impact. From within the enclosure, participants in ceremonies would have been surrounded by earth walls that blocked views of the outside world, creating a separate ritual space removed from everyday landscapes. From outside, the earthworks visible on the hilltop would have been impressive from miles away, a clear sign of human presence and organization. The site includes gaps in the walls that may have served as formal gateways, with some alignments suggesting astronomical significance. Like many earthwork sites, Fort Ancient accumulated gradually over centuries, with different generations modifying and adding to the original design. The Miami River flows 160 miles from Indian Lake to its confluence with the Ohio River at the Indiana border, draining approximately 3,900 square miles of western Ohio. The river occupies a valley carved by glacial meltwater, giving it a channel larger than the modern river seems to need. Like many Ohio rivers, the Miami's flow varies dramatically with seasons, with spring typically bringing high water and floods, while late summer sees the river retreat to a modest stream in many sections. The name Miami comes from indigenous peoples who lived along the river before European settlement, though the pronunciation and spelling have been altered over time. The river supported indigenous communities for thousands of years, providing water, transportation, and food resources. Later, the river helped attract European settlers and powered early industry through water mills built on its tributaries. The Miami's relatively gentle gradient made it suitable for navigation by shallow draft boats, and it became an important transportation route in the early settlement period. The river continues serving multiple purposes today: water supply for cities, recreation, agricultural drainage, and habitat for fish and wildlife. The Miami Valley contains some of Ohio's most productive farmland. The rich glacial soils supplemented by alluvial deposits the river has spread across its floodplain over millennia. Indian Lake sprawls across nearly 5,800 acres in Logan County, serving as the source of the Miami River, though the lake itself is not a natural feature, but rather a reservoir created in 1851 by damming multiple small streams. This makes it one of Ohio's oldest significant artificial lakes, created at a time when large-scale water control projects were just becoming feasible. The dam created a shallow lake, average depth only about 8 feet, that serves multiple purposes including flood control, water supply, and recreation. The lake's shallowness means it warms quickly in summer, making it popular for swimming and other water sports, but it also means the lake is vulnerable to algal blooms and other water quality issues. Extensive development around the shoreline has created a summer resort atmosphere, with cottages, marinas, and beaches crowding what was once a patchwork of small streams and wetlands. The lake's creation transformed the local landscape profoundly. Areas that were once dry land became lake bottom. The pattern of streams changed as their lower reaches were drowned by the rising reservoir. Wildlife adapted to terrestrial or stream habitats, either relocated or perished, while species favoring lake conditions moved in. Today's Indian Lake ecosystem bears little resemblance to what existed before the dam, representing instead a thoroughly engineered landscape shaped to human purposes. The Scioto River travels 231 miles from Auglaize County to Portsmouth, where it joins the Ohio River after draining 6,517 square miles, making it Ohio's longest river entirely within state boundaries. The Scioto's name comes from a Native American word, though the exact meaning is disputed, Various sources suggest it means deer or relates to the river's characteristics. The river flows generally southward through the center of the state, passing through Columbus, where it broadens considerably and becomes a significant feature of the urban landscape. The Sciotos Valley provided a natural north-south corridor through Ohio, and highways, railroads, and settlements naturally followed this route. The river itself has been extensively modified in its urban sections, channelized, diked, and controlled to reduce flooding and accommodate development. Further upstream and downstream from Columbus, the river retains more natural character, meandering through agricultural land and remaining woodlots. The Scioto supports diverse fish populations and provides important habitat for migrating waterfowl, despite the modifications humans have imposed on its channel. The river's watershed encompasses landscapes ranging from flat till plains to the unglaciated hills of southern Ohio, each contributing its character to the water that eventually combines in the Scioto's channel. Big Darby Creek earned designation as one of Ohio's first state and national scenic rivers due to its exceptional water quality and diverse aquatic life, including over 100 fish species, an extraordinary diversity for a stream of its size. The creek flows through largely rural areas in west-central Ohio, draining land that has remained less developed than most of the state. This relative lack of development has protected water quality, allowing the creek to support species sensitive to pollution that have disappeared from more degraded streams. The scenic river designation provides some protection against development that would compromise water quality, though maintaining that quality requires vigilant monitoring and land use management across the entire watershed. Big Darby Creek demonstrates what Ohio's waterways could be: clear water flowing over gravel beds, supporting abundant fish populations and the wildlife that depends on healthy aquatic ecosystems. The creek contains riffles and pools, fast water, and slow, providing diverse habitats that support the remarkable species diversity. Some sections flow through forested valleys where sycamores and silver maples shade the water. Other sections wind through farmland, testing the creek's resilience as agricultural runoff adds nutrients and sediment. The creek's ecological health reflects the cumulative choices made by landowners throughout its watershed, each farm's practices contributing to or detracting from water quality. The 60-mile stretch of Big Darby Creek contains more fish species than any other comparable stream in Ohio, with unusual species like the northern mad tom and big-eye chub indicating pristine habitat conditions increasingly rare in Midwestern streams. These sensitive species serve as indicators of water quality. Their presence tells biologists that conditions are good: clean water, appropriate habitat structure, adequate food supply. Their absence from streams that once held them signals degradation. The northern mad tom is a small catfish, rarely exceeding 4 inches in length, that requires clean gravel substrate and well-oxygenated water. The big-eye chub, similarly, needs specific habitat conditions that disappear when streams are degraded by pollution or channelization. Finding these species in Big Darby Creek confirms that the stream still provides what they need, but their presence is not guaranteed for the future. Each development in the watershed, each farm choosing conventional over conservation agriculture, each impermeable surface added, affects the creek downstream. Water quality in streams reflects land use across their entire watersheds, making protection a complex challenge requiring cooperation among many landowners. Big Darby Creek's exceptional fish diversity represents not just biological richness, but also successful conservation. People making choices that maintain the creek's health despite the pressures of modern development. Lake Hope State Park sits within a valley in Vinton County that contains remnants of a once thriving charcoal iron industry, where 30 sandstone furnaces operated throughout the 1800s, now slowly being reclaimed by returning forest. These furnaces, built from locally quarried sandstone, are impressive structures, massive stone walls designed to contain the intense heat needed for iron smelting. The furnaces converted iron ore into pig iron using charcoal as fuel, and the demand for charcoal devastated the surrounding forests. Producing charcoal required cutting vast quantities of hardwood, stacking it in earthen mounds, and allowing it to smolder slowly in oxygen-limited conditions that converted wood to pure carbon. Each furnace consumed forests for miles around, and the Vinton County landscape was stripped nearly bare during the iron industry's height. When the iron industry declined due to changing technology and depleted local resources, the furnaces were abandoned and the forests began returning. Today, second-growth forest covers most of the county, with trees now 80 to 100 years old, creating what looks like mature woodland. But the land remembers the industry. The furnace ruins still stand, their sandstone blocks fitted with skill that has outlasted their purpose. The forest is too young to have large trees, and charcoal hearth sites still show as circular flat areas where nothing grew for decades after the fires. The Zaleski State Forest covers 28,000 acres of the unglaciated Allegheny Plateau, where steep ridges and narrow valleys create topography more reminiscent of West Virginia than typical Ohio landscapes. This is hill country, with elevation changes of 400 feet or more from ridgetop to valley floor. The ridges run in parallel lines, following the structure of tilted sedimentary layers, sandstone caprock creating the ridgetops, shales, and softer rocks exposed in the valleys. Roads wind through the valleys or laboriously climb the ridges, unable to take the direct routes possible in flat terrain. The forest itself is mixed hardwood, predominantly oak and hickory on the ridges where soils are thin and droughty, more diverse species in the valleys where moisture accumulates. The unglaciated terrain means the soil developed over millions of years rather than being deposited by ice thousands of years ago. This older soil is more weathered, more leached of nutrients, creating growing conditions that differ from glaciated Ohio's rich till. The forest's age varies. Most areas were logged in the 19th and early 20th centuries, so the trees are relatively young. But scattered old trees persist in spots too steep or remote to be worth logging, survivors that link the modern forest to what existed before European settlement. Tar Hollow State Forest and Park protects 16,000 acres of rugged terrain where elevations vary by more than 500 feet within single valleys, creating habitat diversity that supports species like timber rattlesnakes rarely found elsewhere in Ohio. The timber rattlesnake is Ohio's largest venomous snake, reaching lengths of 4 feet or more, but it's also one of the most docile, avoiding confrontation whenever possible. These snakes require extensive undisturbed forest with rocky outcrops for hibernation dens, habitat that has become scarce across most of Ohio. Tar Hollow's rugged topography and large blocks of forest provide what they need. The snakes den communally in deep rock crevices that remain above freezing through winter, with dozens of individuals sometimes using the same den site generation after generation. In spring, they disperse through the forest to hunt, their diet consisting primarily of small mammals. By fall, they return to the den sites, following scent trails and perhaps memory to find their way back to the same rocky hillsides. The persistence of timber rattlesnakes in Tar Hollow indicates the forest is large enough and wild enough to support apex predators that need extensive range. Their presence is a mark of ecological health, though it also means hikers need to watch where they step. especially near rocky areas on south-facing slopes where the snakes bask in spring and fall. Wayne National Forest stretches across 244,000 acres, spread through 3 separate districts in southeastern Ohio, making it the state's only national forest and protecting some of the most topographically diverse terrain in Ohio. The forest is not a continuous block, but rather a patchwork of federally owned lands interspersed with private property, creating a complex ownership pattern that affects management and access. The 3 districts, Athens, Marietta, and Ironton, each have distinct characteristics reflecting their specific geologies and histories. The Athens unit includes areas of high-quality forest on steep terrain, including old-growth remnants. The Marietta unit contains a mix of forest and former surface-mined lands in various stages of reclamation. The Ironton unit borders the Ohio River, its forests growing on steep hillsides that drop directly to the water. All 3 districts share the characteristic rugged topography of unglaciated southeastern Ohio, with narrow, winding valleys separating parallel ridges. The forest supports black bear, which have recolonized the region in recent decades after being absent for over a century. White-tailed deer are abundant, as are wild turkeys. The forest's ecological value extends beyond its federally owned acres, as the protected lands provide core habitat that supports wildlife populations throughout the region. Within Wayne National Forest, the Archer's Fork area contains old-growth forest with trees exceeding 400 years old, survivors of both the logging era and the region's rugged terrain that protected them from easy access. These ancient trees, primarily oaks and hickories, represent living connections to the pre-settlement forest that once covered all of southeastern Ohio. Their trunks are massive, 3 feet or more in diameter, their bark deeply furrowed by centuries of growth. Their canopies tower over younger surrounding trees, claiming the sunlight that shorter trees can only glimpse through gaps. These old trees create their own ecosystems. Dead branches provide nesting sites for woodpeckers and owls. Loose bark shelters insects and bats. The tree's roots create soil stability, preventing erosion even on steep slopes. When these old trees eventually fall, they'll create gaps in the canopy that allow younger trees to grow, and their slowly decaying trunks will nurture seedlings and provide habitat for salamanders, fungi, and countless invertebrates. The old-growth forest has a different feel from younger woods, more vertical structure, more dead wood in various stages of decay, more complexity in the understory. Walking through old growth, you're surrounded by living history, by organisms that existed before European settlement, that have persisted through centuries of human-caused change in the surrounding landscape. The Dysart Woods in Belmont County preserves 50 acres of old-growth forest, where oaks and tulip poplars reach heights over 150 feet and diameters exceeding 4 feet, representing pre-settlement forest conditions that once characterized much of Ohio. This small remnant survived because it occupied a steep hillside difficult to log with the technology available when surrounding forests were being cut. The trees here include white oak, red oak, and tulip poplar that are 300 to 400 years old, their size testifying to the growing conditions and time they've experienced. The forest structure differs dramatically from the younger second growth covering most of Ohio. Multiple canopy layers exist, the towering old trees forming an upper canopy, smaller trees filling the mid-level, and saplings and understory plants occupying the forest floor. Dead standing trees, called snags, provide crucial habitat for cavity-nesting birds. Fallen logs in various stages of decay carpet the forest floor. their wood softening as fungi and insects break it down, returning nutrients to the soil. The diversity of plants and animals in old-growth forest exceeds that of younger forest because the structural complexity provides more ecological niches. Some species, certain salamanders, fungi, and insects, may be restricted to old-growth conditions and absent from younger forest. Dysart Woods offers a glimpse of what all of Ohio's forests once were, and what they might become again, if given centuries to recover from logging. Clear Creek Metro Park contains a rare stand of Canada hemlock trees far south of their typical range, surviving in cool, moist gorges where temperature and humidity approximate conditions hundreds of miles northward. The eastern hemlock's main range extends through the northern states and Canada, with Ohio lying at the southern edge of its distribution. Within Ohio, hemlocks occur in scattered locations where local conditions compensate for the generally warmer climate. Cool gorges with north-facing slopes, constant moisture from seeps and streams, and shade that moderates temperature create microclimates suitable for these northern trees. The hemlocks at Clear Creek grow slowly in conditions at the edge of their tolerance. Their growth rings tight and wood-dense. These trees live long lives. Individual hemlocks can exceed 400 years, but they reproduce with difficulty this far south. Seedlings need specific conditions to survive, and climate warming may make those conditions increasingly rare. The hemlock stands are relict populations, remnants of the cooler climate that prevailed immediately after the glaciers retreated. As temperatures warmed, hemlocks retreated northward, except in these special microsites where conditions remained suitable. These isolated southern populations may contain genetic diversity absent from northern populations, representing adaptations to warmer conditions that could become important as climate continues changing. For now, the hemlocks persist, their dark evergreen foliage distinctive among the deciduous oaks and maples that dominate Ohio forests. Nelson Kennedy Ledges State Park features vertical cliffs and slot canyons barely wide enough to pass through, carved by erosion along vertical cracks in Sharon conglomerate caprock that resisted horizontal erosion affecting softer underlying layers. The park's landscape feels different from most Ohio terrain, more vertical, more confined, with passages between rock walls that tower overhead. The conglomerate, with its embedded rounded pebbles, forms resistant ledges that stand as cliffs, while softer sandstones and shales below erode away. Vertical joints, cracks that developed in the rock long ago, provided weaknesses that erosion exploited, widening them into passages. Some joints opened into parallel slots just a few feet apart, creating walls of rock barely thick enough to be stable. Walking through the ledges requires navigation through this maze of stone, squeezing through narrow passages, climbing over fallen blocks, ducking under overhangs. In places, the rock walls lean together overhead, creating tunnels that block the sky. The sense of enclosure is profound, the stone pressing close on all sides. Moss and ferns grow where moisture collects in crevices. In winter, ice forms spectacular columns and curtains where water seeps through the rock and freezes. The ledges attract rock climbers who appreciate the vertical faces and the solid conglomerate that accepts protection well. The ledges at Nelson Kennedy create narrow passages with colorful names like Fat Man's Peril and Squeeze Box, where visitors must turn sideways and sometimes remove backpacks to navigate between walls just 18 inches apart. These passages formed where erosion widened vertical joints in the conglomerate, creating parallel walls separated by gaps that vary from a few feet to barely more than a foot. The narrowest passages require some confidence to enter, as you commit to squeezing through tight spaces with solid rock on both sides. Most passages have uneven floors, littered with fallen rock fragments, requiring careful foot placement as you edge through sideways. The passage names reflect both the challenge of navigation and the playful spirit of early visitors who explored and named the features. Fat Man's Peril suggests exactly what it is, a squeeze that tests whether you can fit through. Squeeze Box is perhaps even tighter, requiring slim builds and some flexibility. These features form one of Ohio's most unusual landscapes, a place where geology created confinement rather than the openness typical of most state parks. The conglomerate walls show their composition clearly. Rounded quartzite pebbles embedded in sandstone matrix, evidence of ancient rivers that deposited these stones 320 million years ago, never imagining they would someday form passages that humans would squeeze through for recreation and challenge. Headwaters Park in Hocking Hills protects the actual source springs of the Hocking River, where water first emerges from underground aquifers in a small ravine before beginning its 102-mile journey to the Ohio River. The springs bubble up from cracks in the bedrock, groundwater that has filtered through porous sandstone layers, finding its path to the surface here rather than elsewhere. Why this particular location becomes the source is determined by subtle variations in geology, the arrangement of permeable and impermeable rock layers that channel groundwater to emerge at this spot. The water is cold year-round, fresh from its underground residence where seasonal temperature variations never penetrate. The springs flow constantly, their rate varying somewhat with regional groundwater levels, but never ceasing completely even during severe droughts. From these modest beginnings, the Hocking River grows as tributaries join it, each adding volume, until by the time it reaches the Ohio River, it's a substantial stream. But here at the source, the river is just beginning, water emerging from stone, starting a journey that will carry it through forests and gorges, over waterfalls and through valleys, eventually contributing its molecules to the Ohio, the Mississippi, and ultimately the Gulf of Mexico. Every great river starts somewhere, often surprisingly modest, and the Hocking begins here in this protected ravine where springs seep from ancient sandstone. The bedrock beneath most of Ohio dips gently eastward at approximately 20 to 40 feet per mile, creating a gradual tilt across the entire state that's invisible at the surface, but fundamental to understanding Ohio's geology. This eastward dip means that as you travel from west to east across Ohio, you're moving down through geological time, with progressively older rock layers exposed at the surface. The tilt resulted from subtle warping of the Earth's crust over millions of years, possibly related to the weight of sediment accumulated in the Appalachian Basin to the east. The angle is so gentle that standing on the ground you'd never detect it. The surface topography, shaped by glaciers and rivers, overwhelms the subtle bedrock tilt. But drill beneath the glacial deposits, and you'd find the bedrock layers all slanting consistently eastward like pages in a tilted book. This structure affects where oil and gas accumulate, where aquifers exist, which rock types appear at the surface in different locations. The dip is one of those fundamental geological patterns that shapes everything else, determining where limestone is available for quarrying, where sandstone forms cliffs, where shale creates valleys. It's the hidden architecture underlying the visible landscape, the structure upon which everything else is built. This eastward dip means Cincinnati's surface bedrock is about 100 million years younger than Cleveland's, with Cincinnati built on Ordovician limestone, formed approximately 450 million years ago, while Cleveland sits on Devonian shale and sandstone, formed between 350 and 400 million years ago. The 100 million year age difference represents an enormous span of geological time, longer than the entire age of dinosaurs, longer than the time since their extinction to the present. During that 100 million years, sea levels rose and fell repeatedly, continents drifted, life evolved from simple marine organisms to the first terrestrial plants and animals. All this history is compressed into the vertical distance between Cleveland's bedrock and Cincinnati's, made accessible horizontally by the bedrock's gentle eastward tilt. When you drive across Ohio, you're not just crossing distance but also time, moving through a chronology written in stone. The landscape doesn't show this clearly because glaciers and rivers have reshaped the surface, but beneath the soil and till, the ancient pattern persists. Older rocks to the east, younger rocks to the west, all tilted together in their gentle eastward dip. This arrangement makes Ohio a natural laboratory for studying sedimentary geology, with layers that elsewhere would require deep drilling available here within reach of the surface. The Tees River once flowed across central Ohio, roughly where Interstate 70 now runs, draining northwestward toward the Great Lakes region, before glaciers obliterated its valley and forced drainage to reorganize into today's river systems. The Tees was ancient even by geological standards, having carved its valley over millions of years through bedrock that now lies buried beneath glacial deposits. The river's course has been reconstructed through drilling records that penetrate the glacial till and encounter the valley fill. Water-worn gravels and sands that once formed the river's bed, now buried hundreds of feet below the modern surface. The Tees River was substantial, comparable to the modern Ohio River in size, and it drained a vast area extending from North Carolina through West Virginia, Ohio, and Indiana. When glaciers advanced into Ohio, they blocked the Tees River's northward flow, creating temporary lakes that eventually overflowed and cut new drainage routes. The river's valley was filled with glacial debris, buried so thoroughly that its existence was unknown until 20th century drilling and geophysical surveys revealed it. Now Interstate 70 follows roughly the same route the Tees once carved, taking advantage of the gentle topography above. The buried valley, drivers passing over an ancient river's grave without knowing it, lies beneath them, its water long since diverted to other channels. Buried beneath hundreds of feet of glacial till, the ancient Tees River Valley is now known only through drilling records and geophysical surveys that reveal its presence like an archaeological excavation reveals buried cities. Where the valley lies shallow, water wells encounter the valley fill gravels, which often form excellent aquifers. Where it lies deeper, only oil and gas drilling reaches it, the drill logs recording the sequence of glacial till, then the distinctive water-worn gravels of the ancient river, then bedrock below. The valley's depth varies depending on how much glacial material accumulated above it. In some places, the Tees Valley lies just 50 feet below the surface. Elsewhere, it's buried under 300 feet or more of glacial deposits. Mapping the buried valley requires piecing together information from scattered drill holes, like reconstructing a jigsaw puzzle with most pieces missing. The result is a ghostly map of a river that flowed for millions of years and then vanished, erased from the landscape but preserved beneath it. The Tees represents what geologists call a preglacial drainage system, patterns of rivers and streams that existed before the ice ages and were so thoroughly disrupted by glaciation that entirely new drainage systems emerged. Most of modern Ohio's rivers are geologically young, existing only since the last glacier retreated. The Tees, by contrast, was ancient, and now it's gone except as buried evidence that patient investigation can reveal. The Findlay Arch represents a subtle dome in the bedrock underlying northwestern Ohio, a gentle upward bulge in the sedimentary layers that brought Silurian age limestone closer to the surface. This slight uplift, barely detectable without careful surveying, created conditions that trapped oil and natural gas in reservoir rocks along the arch's flanks. Petroleum, being less dense than water, migrates upward through porous rock layers until it encounters an impermeable barrier that stops its movement. The Findlay Arch provided such a trap, with tilted limestone beds holding oil and gas that couldn't migrate further. When drillers in the 1880s discovered oil in northwestern Ohio, it sparked Ohio's first oil boom, with wells rapidly drilled throughout the region. The fields were not enormous by later standards. Ohio never rivaled Texas or Pennsylvania in total production, but they were significant locally and demonstrated that oil could be found in the Midwest. The Findlay Arch's role in this discovery shows how subtle geological structures can have major economic consequences. An uplift of a few hundred feet across many miles, barely perceptible at the surface, nevertheless altered the subsurface geometry enough to create natural traps for petroleum. The arch continues to be studied today, as modern technology allows more complete exploitation of remaining oil and gas reserves through techniques unavailable to 19th century drillers. Bowling Green State University's campus sits atop an ancient Lake Erie beach ridge, explaining its noticeably higher elevation compared to the surrounding terrain and its better drainage compared to the swampy lowlands that characterized much of northwestern Ohio before agricultural development. The ridge formed as a beach deposit during one stage of the glacial lake that preceded modern Lake Erie. Waves sorted sand and gravel along the shoreline, building a raised ridge that remained after the lake level dropped. The ridge isn't dramatic, perhaps 10 to 20 feet higher than adjacent land. But this modest elevation made enormous difference for early settlement. The ridge provided dry ground through the Great Black Swamp, a natural route that travelers preferred over the sodden lowlands. When the university was established, its location on the ridge ensured good drainage and stable foundations, advantages that continue today. Walking across campus, you might not recognize you're on an ancient beach unless you know what to look for. But topographic maps show the ridge clearly, a gentle rise extending for miles across the landscape. The ridge is one of several that stripe northwestern Ohio, each representing a different stage of Lake Erie's predecessor. These features are subtle but persistent, still affecting development patterns and land use thousands of years after the lakes that formed them shrank to Erie's modern dimensions. The Portage Lakes in Summit County form an interconnected chain of 8 natural glacial lakes and reservoirs covering about 2,100 acres, created when blocks of glacial ice buried in sediment melted and left depressions that filled with water. These kettle lakes, as geologists call them, formed when the last glacier retreated from this area roughly 14,000 years ago. The glacier didn't melt evenly or completely. In places, large blocks of ice broke off and were buried by glacial sediment accumulating around them. These ice blocks, insulated by the surrounding material, took decades or centuries to melt completely. When they finally did, the sediment that had surrounded them collapsed into the voids, creating depressions. Groundwater and surface water filled these depressions, creating lakes. The Portage Lakes vary in size and depth, reflecting the size of the original ice blocks and the amount of sediment that accumulated. Some are quite deep for Ohio lakes, 40 feet or more in places. Others are shallow, gradually filling with aquatic vegetation and sediment. The lakes have been modified over time, with dams and channels connecting them more extensively than their natural condition. But their origin remains glacial. Their legacies of ice, bodies of water, occupying voids left by melted ice from a glacier that retreated when Ohio's landscape was tundra rather than forest. East Harbor State Park on the Marblehead Peninsula protects one of Lake Erie's largest natural bays, a shallow 1,800-acre embayment that serves as critical habitat for migrating waterfowl and spawning fish. The bay is separated from the main lake by a narrow barrier beach, creating protected waters that remain calmer than the open lake. The shallow depth, rarely more than 10 feet, means the bay warms quickly in summer and supports abundant aquatic vegetation. This vegetation provides food and shelter for fish, including species that spawn in the bay's shallow waters, where their eggs and fry find refuge from predators common in deeper water. In spring and fall, the bay hosts enormous numbers of migrating ducks, geese, and other waterfowl, which rest and feed here during their journeys between breeding grounds and wintering areas. The bay's ecological importance extends beyond its borders, as fish that spawn here eventually move into the main lake, and birds that rest here continue migrations that span continents. The bay represents the kind of shallow wetland habitat that once characterized much of Lake Erie's southern shore, but has been largely destroyed by development. East Harbor's protection ensures this habitat persists, providing benefits for wildlife populations that extend far beyond the bay's boundaries. The relationship between protected bay and open lake, between shallow nursery waters and deeper feeding areas, demonstrates the interconnection of aquatic habitats. The Lake Erie Islands consist of Devonian limestone bedrock, the same formation that underlies Detroit and parts of southern Ontario, creating a natural stepping stone connection across the lake that happens to be mostly underwater. The islands are essentially the highest points along a limestone ridge that extends across the lake. Most of this ridge lies submerged, forming the reefs and shoals that make Lake Erie's western basin treacherous for navigation, but excellent for fish habitat. Where the ridge rises above water level, islands form. The limestone itself is approximately 400 million years old, formed in a shallow tropical sea from accumulated carbonate sediments and shell fragments. Later, tectonic forces tilted the rock slightly, and much later, erosion removed overlying layers, exposing the limestone. Glaciers scoured the surface, creating the grooves visible on Kelly's Island and smoothing the bedrock into low, rounded forms. As glacial ice melted and water levels rose, the low areas flooded, leaving only the highest points as islands. The limestone's characteristics, its resistance to erosion, its tendency to form flat surfaces with vertical cliffs at edges, its chemical composition, determine the island's ecology and human use. The stone drains quickly, creating dry conditions despite being surrounded by water. Thin soils support vegetation adapted to drought and exposure. The island's limestone origin connects them geologically to distant places, all part of the same ancient sea floor. North Bass Island remains largely undeveloped despite its 677 acres, supporting only about 35 year-round residents and representing one of Lake Erie's most pristine island ecosystems. The island's development was limited partly by its relative isolation. It's farther from the mainland than Middle or South Bass, and partly by ownership patterns that kept large tracts intact rather than subdividing them for intensive development. The result is an island that still feels relatively wild, with extensive forests, wetlands, and undeveloped shoreline. The limited human population means limited infrastructure, which in turn limits the number of visitors the island can accommodate. This creates a self-reinforcing pattern of low development. The island supports wildlife populations that have been displaced from more developed islands, including nesting birds that require undisturbed habitat. The forests contain trees that have grown for decades without disturbance, creating more mature structure than exists on islands where every acre has been developed. The shoreline includes natural beaches and rocky areas unmodified by seawalls and breakwaters. This relative wilderness is rare among Lake Erie's islands and valuable for both ecological reasons and as a reminder of what the islands once were before development transformed them. North Bass Island's future depends on maintaining the patterns that have protected it so far: large intact ownerships, limited infrastructure, and a community committed to preservation. Rattlesnake Island, despite its ominous name, spans only 85 acres and supports no dangerous snakes whatsoever, earning its name instead from its rattlesnake-like shape when viewed from above or from distant shores. The naming reflects a common pattern in frontier geography, where features received colorful names based on visual resemblance, local legends, or misunderstandings that persist long after their origins are forgotten. The island's actual shape does suggest a coiled snake when seen from certain angles, with the narrow eastern end serving as the head and the broader western portion as the body. The lack of actual rattlesnakes doesn't diminish the name's staying power. Once a place is named, the label tends to persist regardless of accuracy. The island itself is privately owned and supports a small number of seasonal residences, quiet structures scattered among the trees that cover most of the small landmass. The island's size makes it one of the smaller inhabited islands in the Bass Islands group, barely large enough to support the handful of buildings and the small marina that provides access. Being privately owned and small, the island sees little public visitation, remaining somewhat mysterious to most Lake Erie visitors who pass it without landing. The island's distinction lies mainly in its evocative name, a small, geographic curiosity that draws smiles from those who learn the truth behind the threatening label. The western basin of Lake Erie, bordered by Ohio's shoreline, averages just 24 feet deep, but contains the lake's most productive fisheries due to shallow, warm conditions that promote abundant aquatic vegetation and invertebrate life. This productivity makes the western basin vital for Lake Erie's overall fish populations. The shallow water warms quickly in spring, triggering earlier plant growth and insect emergence compared to deeper lake sections. This early productivity provides food for fish when they need it most, during spawning and the critical weeks after hatching, when young fish require abundant, tiny prey. Walleye, yellow perch, and smallmouth bass all spawn in or near the western basin, their eggs and fry benefiting from the warm, food-rich conditions. The basin's extensive beds of aquatic plants provide shelter for young fish and hunting grounds for predators. Mayfly larvae, abundant in the basin's soft sediments, support enormous populations when they emerge in spring and summer. These same conditions that make the western basin productive also make it vulnerable. The shallow water concentrates pollutants rather than diluting them. Nutrients from agricultural runoff accumulate, sometimes triggering algal blooms that can cover vast areas in summer. The balance between productivity and vulnerability makes the western basin both valuable and fragile, requiring careful management to maintain its role as the biological engine driving Lake Erie's remarkable fisheries. Meiji Marsh Wildlife Area on Lake Erie's southern shore hosts more than 300 bird species during migration, with the concentrated shoreline creating a natural funnel where thousands of migrating warblers and other songbirds gather each spring. The phenomenon occurs because the lake creates a barrier that migrating birds prefer not to cross directly. Birds moving north in spring reach the lake's southern shore and tend to follow the coastline rather than striking out across open water, concentrating in shoreline habitats. Magee Marsh, with its extensive wetlands and forest, provides exactly what tired, hungry migrants need: food, water, and shelter. In early May, the marsh becomes one of North America's premier birding destinations, attracting observers from around the world who come to see the concentrations of colorful warblers at eye level in the trees. On peak days, a single morning might reveal 30 or more warbler species, along with thrushes, vireos, tanagers, and other migrants. The birds move through the marsh in waves, feeding intensively to rebuild energy reserves depleted during their night flight north. After a few days of rest and feeding, they continue their journeys, heading to breeding grounds in Canada and the northern United States. The annual return of migrants to Magee Marsh is predictable enough that the area hosts festivals celebrating the arrival of birds that connect this place to tropical wintering grounds and northern forests through their twice-yearly travels. The Black Swamp Bird Observatory Boardwalk at Magee Marsh extends nearly a mile through restored wetland forest, creating opportunities to observe migrating birds at eye level in the tree canopy during the peak of spring migration. The boardwalk elevates observers above the marshy ground, allowing access to areas that would otherwise be impassable during the high water of spring. The elevated perspective puts visitors at the same level where many birds feed in the lower canopy, offering views that are impossible from ground level. The boardwalk winds through forest dominated by trees adapted to wet conditions: silver maples, cottonwoods, willows, their branches often hosting feeding warblers so close you can observe them without binoculars. The structure is carefully designed to minimize impact on the habitat while maximizing opportunities for observation and photography. Viewing platforms at intervals allow groups to gather without crowding the narrow walkway. Interpretive signs provide information about the species likely to be encountered and the ecology of Great Lakes coastal wetlands. The boardwalk's popularity during peak migration requires management to prevent overcrowding that would disturb the very birds people come to see. But when used respectfully, the boardwalk provides access to a natural spectacle: the annual pulse of life moving north, millions of birds following ancient routes, pausing briefly in this marsh before continuing journeys that span continents and connect ecosystems from tropical forests to boreal wilderness. Ottawa National Wildlife Refuge encompasses 9,000 acres of marshland restoration, where what was once drained farmland is being returned to wetland habitat, reversing more than a century of agricultural transformation. The refuge's creation and ongoing restoration represent a philosophical shift in how we value wetlands. The land that now composes the refuge was drained in the late 19th and early 20th centuries, part of the massive effort to convert the Great Black Swamp and Lake Erie marshlands into farmland. The wetlands were seen as wastelands, areas that needed to be improved through drainage. For decades, crops grew on these drained fields, but the land remained challenging for agriculture, poorly drained despite the ditches, prone to flooding, requiring constant management. Eventually, recognition grew that these wetlands were more valuable as wetlands than as marginal farmland. Beginning in the mid-20th century, lands were acquired for the refuge and restoration began. Dikes were built to hold water. Drainage tiles were blocked or removed. Native wetland plants were encouraged to return. The transformation back to wetland doesn't happen instantly. Decades of agriculture changed the soil, introduced invasive species, and eliminated many native plants and animals. But gradually the refuge is recovering, providing habitat for migrating waterfowl, marsh birds, fish, and countless invertebrates. The restoration continues, each year bringing the refuge closer to the functioning wetland ecosystem that existed before drainage. The Great Miami River, not to be confused with the Little Miami, flows 170 miles through western Ohio, joining the Ohio River at the Indiana border after draining 3,630 square miles of primarily glaciated terrain. The Great Miami occupies a valley carved by glacial meltwater, giving it a channel size that seems too large for the modern river, evidence of the much greater flows that occurred during ice sheet melting. The river's watershed encompasses some of Ohio's most productive agricultural land, the rich glacial soils supporting intensive farming that generates agricultural runoff affecting water quality. The river itself has been extensively modified for flood control through levees, channelization, and a series of dams that reduce flood peaks and maintain minimum flows during dry periods. These modifications reflect the river's history of devastating floods, particularly the Great Flood of 1913, that caused immense damage throughout the Miami Valley and led to creation of one of the nation's first comprehensive flood control systems. The engineered river is safer but less ecologically diverse than the natural river it replaced. Channelization reduced habitat complexity. Dams blocked fish migration routes. The steady flows maintained by flood control eliminate the natural variation between high and low water that many native species require. The Great Miami demonstrates the trade-offs inherent in river management, gaining flood protection and reliable water supply while losing natural function and native biodiversity. Cedar Creek Lake and State Park covers 7,900 acres of reservoir created by damming Cedar Creek in 1978, with the lake bottom submerging a complete 19th-century village whose stone foundations occasionally emerge during severe droughts. The village, called New Burlington, was home to several hundred people before the dam project required its abandonment and eventual inundation. Houses were moved or demolished, roads were removed, and the valley was cleared before flooding began. But the stone foundations of houses, shops, and public buildings were too expensive to remove completely, so they were left in place, now buried under up to 50 feet of water depending on lake level. During extreme droughts, when the reservoir draws down dramatically, these foundations emerge from the mud, ghostly remnants of a community that ceased to exist. People who once lived in New Burlington returned to see their former home's foundations, walking on lake bottom that was village streets. The submerged village represents the human cost of water projects. Families displaced, communities dissolved, histories literally buried. The lake provides recreation and flood control benefits to thousands, but it did so by erasing a place where generations had lived. The foundations that emerge during droughts remind us that beneath the reservoir's surface lies not just water, but also memory. The physical traces of lives lived before the valley was deliberately drowned to serve purposes deemed more important than preserving the community that called it home. The gorge below Cedar Creek Dam exposes Ordovician limestone and shale layers approximately 450 million years old, where fossil hunters regularly discover complete trilobites, brachiopods, and ancient marine creatures preserved in stone. The dam's construction and the regular water releases scour the bedrock clean, constantly exposing fresh rock surfaces where fossils are visible. The limestone formed in a shallow tropical sea, and the fossils are the actual remains of organisms that lived in that ancient ocean. Trilobites, extinct arthropods related to modern horseshoe crabs, are particularly common in these beds, their segmented exoskeletons often preserved in beautiful detail. Brachiopods, clam-like animals that filtered food from the water, occur in such abundance that some rock layers consist almost entirely of their shells. These fossils aren't just scientific curiosities, but windows into a vanished world, a time when this location lay south of the equator beneath warm seas. The rock itself tells stories through its layers, each bed representing a different period of deposition, different conditions in the ancient sea. Some layers are pure limestone, accumulated from carbonate mud and shell fragments. Others contain more clay and silt, washed in from distant land masses. Reading these layers requires patience and knowledge, but the story they tell spans millions of years of Earth history, preserved in stone now exposed by the incidental action of water released from a modern dam. Ohio's 312-mile length from east to west exceeds its 220-mile width from north to south, creating a state that stretches further horizontally than vertically, shaped as much by political compromise as by geographical logic. The borders reflect decisions made in the late 18th and early 19th centuries, when Ohio was being organized as a territory and then as a state. The northern border follows Lake Erie's shoreline, a natural boundary. The southern and eastern borders follow the Ohio River, another natural feature. But the western border is an arbitrary line, straight from north to south, reflecting political agreements between Ohio, Indiana, and Michigan, rather than any geographical feature. The northern border's position was contested in the Toledo War, a bloodless conflict between Ohio and Michigan over a narrow strip of land, including the vital port of Toledo. Ohio won that dispute, gaining territory that gave it better lake access. The result is a state elongated east to west, connecting the Appalachian region in the east with the beginning of the Midwest Plains in the west, encompassing both glaciated and unglaciated terrain, both industrial and agricultural regions, both river and lake systems. Ohio's shape encapsulates its identity as a transition zone, a place where eastern and western characteristics meet, where natural and political geography combine to create boundaries that seem inevitable now, but resulted from choices and compromises that might have gone differently.